A warm morning to one and all. Welcome aboard, everyone, to the third International Conference on Advances in Naval Architecture and Ocean Engineering, sponsored by Cochin Shipyard Limited, Conceptia Marine, Ares Energy, Essando Maritime, Capital Ship Solutions, and Stigon. Surging ahead since 1975, the department is committed to creating a new and dynamic generation of naval architects and ocean engineers to meet the requirements of the Indian shipbuilding industry, classification societies, R&D organizations, the Indian Navy, and related organizations. iCANOE will be a vibrant intellectual platform for academicians, engineers, research, and industry experts and maritime professionals. The topic and content coverage of the conference will provide insights that pave the way for sustainable future in maritime field. On the dais, we have the Honorable Vice Chancellor of CUSAT, Professor Dr. Junaid Bushiri, our Chief Guest of the Day, Mr. Yoichi Iga, Regional Manager of Middle East and South Asia, Class NK Japan, Mr. Sumitan Sambat, who is the General Manager of Class NK Japan, Professor Dr. Madhyaragan, HOD Department of Ship Technology, and Dr. K. Shivaprasad, Professor Department of Ship Technology and Interim Vice Chancellor of Kerala Technological University. We also have Dr. Satish Babu PK, Associate Professor, along with Rajesh P. Nair and Dr. Hasina K, the conveners of the event. We will begin the event with the spiritual note. I request everyone to kindly rise for the prayer. Mr. Pranav will lead us in the prayer.
സ്നേഹമാം തിരുദീപമേ അണയാതെ നീ തെളിയണമേ മാർഗമായി മണിഗീതമായി തിരുനാമമായി ജപമന്ത്രമായി നാമമായി ജപമന്ത്രമായി കണ്ണിലെ തെളിനാളമായി ഇരുൾ മായ്ക്കുവാൻ വരമേകണേ എന്നിലെ കരുണാമൃതം കടാക്ഷമായി നിറയണമേ നന്മയാ നിറയണമേ സ്നേഹമാം തിരുദീപമേ അണയാതെ നീ തെളിയണമേ മാർഗമായി മണിഗീതമായി തിരുനാമമായി ജപമന്ത്രമായി നാമമായി ജപമന്ത്രമായി.
Thank you, Pranav. The department is very grateful, every one of you, for giving your time and effort to be here. To express our sincerest regards and extend a warm welcome, I call upon Dr. Hasina K, convener of this event, to welcome the gathering.
Good morning to one and all. Actually, it is a moment of great pride for the Department of Ship Technology as we gather here for the third International Conference on Advances in Naval and Ocean Engineering, iCANOE 25. So this two-day workshop, as you all informed, it brings together academicians, researchers, industry leaders, and maritime professionals to exchange ideas, to share their research outcomes, and discuss the sustainable innovations that is shaping the maritime sector. iCANOE 25 is especially meaningful as it comes in the lead up to the Golden Jubilee year of Department of Ship Technology, a milestone that we celebrated with immense pride in the last December. So it is worth recalling the success of the previous two editions of the conference. And now iCANOE 25 proudly extends its legacy through 4 major themes related to naval and ocean engineering: ship hydrodynamics, numerical structural analysis, materials and corrosion, and artificial intelligence and digital transformation in the maritime sector. So we will also have 5 keynote lectures delivered by eminent professors and industry experts from the field. Okay, with this, I will now proceed with my responsibility for this session. So first and foremost, I extend a warm welcome to the president of today's function, Professor Dr. Madhyaragan A, the head of the Department of Ship Technology. Sir, it is our privilege to welcome you. My respectful and heartfelt welcome to our Honorable Vice Chancellor of Cochin University of Science and Technology, Professor Dr. Junaid Bushri, who has graciously consented to inaugurate this conference. Sir, we are deeply honored by your presence. It is my privilege to warmly welcome our chief guest, Mr. Yoshi Ga, Regional Manager for the Middle East and South Asia, Class NK, Japan. Sir, it is a pleasure and honor to welcome you to this event. I'm pleased to welcome Mr. Sumitran Sambath, General Manager, Class NK, Japan. Sir, we are very happy to have you with us in this conference too. So we all are delighted to welcome Professor Dr. Shiva Prasad, Professor, Department of Ship Technology, and the Honorable Vice Chancellor of APJ Abdul Kalam Technological University. So we are privileged to have you with us. And we extend a warm and respectful welcome to all our senior professors who have joined us today. A cordial welcome to all our keynote speakers, session chairs, paper presenters, industry delegates, alumni representatives from DOSTAS, faculty members, staff, research scholars, and enthusiastic volunteers of SNAS and CUSAT. And all your presence add immense value to this conference, iCANOE 25. And I extend a warm welcome to all our sponsors. Your support and collaboration have played a vital role in enabling this conference. So once again, a warm welcome to all. May iCANOE 25 be 2 days of learning, sharing, and inspiration. Thank you.
Thank you, Hasina ma'am, for warmly welcoming our esteemed guests. It is my honor to invite the driving force behind this event. I kindly request our head of the department, Professor Dr. Madhyaragan, to address the gathering.
Good morning, all. Honorable Vice Chancellor, Dr. Junaid Bushri, sir. The chief guest of the day, Mr. Yoshi Iga, Regional Manager of Middle East and South Asia, Class NK. Mr. Sumitran Sambath, General Manager, Class NK. Dr. Satish Babu, PK, Associate Professor. Dr. K. Shiva Prasad, Vice Chancellor of KTU, and others, members present here. Convener of the conference, Dr. Rajesh P. Nair, Dr. Kasina, professors, members of the family of the Department of Ship Technology, students, teachers, non-teaching staffs, technical staffs, and delegates, participants, and sponsors. It's a matter of immense pleasure that we are conducting the third edition of the International Conference on iCANOE. This very word was coined by Dr. Professor K. Shiva Prasad. We had a lot of deliberation on this to coin this word. It's an idea of Dr. Shiva Prasad sir, who has made this the event when he was there in the department before joining the KTU. And we are very much grateful to the overwhelming support from various institutes, R&D organization, industries, classification societies, alumni, and the research community, and others who are supporting this event. In fact, the quality of research papers have been selected in tune with the advances in the domain of naval and ocean engineering. I'm sure that this conference, the speakers of this conference will enlighten and enrich the audience and the researchers so that they can grow much faster and much better in their respective domain. I express my sincere appreciation to convener of the conference, Dr. Rajesh, Dr. Hasina, for their painstaking effort for conducting this wonderful event. I also congratulate the Class and Best Projects awardees and also the Professor Dr. K. Suprasad for having served for 30 years and more than that, and yes, given immense contribution to this department. So I hope that you will continue to support the department in the days to come. So come to the achievement of the department, we have got re-accredited with NBA recently. This is up to 2028. And also the placement record has been 100% so far. Even this year also we are going to fetch 100% placement. And we have also got under the leadership of the Dr. Satish Babu sir and Dr. Ebenezer, Dr. Junaid sir, Vice Chancellor of this department, university, who has brought major projects, CSR projects from CSL and also from MDL. So this would be a great space for the department in terms of the research and also the developments. We have been doing consultancy and research projects in various areas, and we have also encouraging our students to write the GATE every year. And Dr. Krishnamurthy sir has taken effort to bring the marine engineering naval architecture field into this so that our students can get qualified in the GATE in the last couple of years. And our alumni support is very strong in terms of the contribution to the department. And in fact, the Indian Navy also has given their maximum support to the department to conduct the courses in time. So the major challenge we face is that the faculty shortage. So I urge the Honorable Vice Chancellor to take initiative to appoint faculty members in the coming days. So man is by nature is a goal-driving being. He has to made to function. Otherwise, there is no growth in future. So our goal is to strive continuously in making our department in front line so that we can progress further. It is set of sail, not the direction of wind, that determines which way we will direct our visions. So I wish the conference a grand success and look forward to a positive outcome. Thank you.
Thank you, sir. It is a privilege to welcome a remarkable individual whose dedication and leadership have been pivotal to the functioning of our university. Professor Dr. Junaid Bushiri, Honorable Vice Chancellor of CUSAT, has kindly graced us with his presence. He is a distinguished academician with over 2 decades of expertise and renowned background in the field of electronics. His vision and contributions have played a significant role in shaping the university's progress and future. It is my proud privilege to welcome you, sir, for the inauguration and the inaugural address.
A very warm good morning to all and all. Respectful chair of this session, Professor Madhiyagan, head the Department of Ship Technology, chief guest of the day, Mr. Yoichi Igasan from NK, Professor, respectful Professor Shiva Prasad, Vice Chancellor, Kerala Technological University, Mr. Sampath from NK, Dr. Hasina, Dr. Satish Babu, Dr. Senthil Prakash, Dean Faculty of Engineering, dear faculties, dear students, and dear participants of this conference. Indeed, it is a great pleasure and privilege for me, as far as myself is concerned, the Department of Ship Technology, it is one of the oldest departments in this kind in India, and particularly in Cochin University of Science and Technology. It is organizing an international conference on advancements in naval and ocean engineering, ICANOE 25. So all of us, particularly people, those who are assembled here, belongs to the field of the community of the naval community or belongs to the ocean engineering community. So I need not have to explain the importance of these two advanced topic. It is very important as far as the development of a place is concerned. Those countries which have a highly advanced techniques and technology, they could have to produce maximum GDP because of their expertise in naval engineering as well as the ocean engineering. We know about the 90% of the goods transport all over the world is carried out through the ship only. The topic is focused on ocean and naval engineering. You know the meaning of the ocean. It's the topic of our discussion and the theme of our conference is like an ocean. It is not a simple thing. We can see so many beautiful things on the surface of the ocean, but if you go the deep, it is not the same. It won't be repeated in the deep. So there is a lot of difference between the surface and the deep of the ocean. So we have to develop new technologies to meet the challenges which is emerging in the field of these two naval architecture and the ocean engineering. This is not limited to a particularly simply designing a naval system, but it should be possible only with the collaboration between the people working in different areas of science and basic science and technology. That means you should have to collaborate with people having knowledge in chemical engineering, and maybe with the people with the mechanical engineering and electronics engineering, communication engineering, and so on. So there are a lot of challenges we have to face with respect to the developing sensors for the proper fruitful navigation of the ships, and also the better communication and the safety of the safety aspects are concerned, and as well as we have to consider the environmental aspects, and we have to develop new technologies to develop new fuels for the ship navigation and so on, and communication. All are the challenges what we have to address in coming years. So our responsibility is very huge as far as a nation is concerned and humanity is concerned, because the role what we are playing in this field, that will eventually beneficial for the entire society of the world. So our responsibility and role is a very responsible role we have to play in coming years. Of course, our department, Ship Technology Department of the Cochin University of Science and Technology is as I mentioned earlier, it is one of the oldest department. It started in the year 1975. It's produced so many alumni. We know several of the alumni of the ship technology is working in different very big ship manufacturing companies all over the world. So particularly in our Cochin shipyard, MD, Sri Madhu Nair, he is also alumni of the Cochin University, and also the MD of the Bombay Mazagon Dock, Jagmohan, he is also alumni of the Cochin University, and our the professor of the ship technology, Professor Shivaprasad, he's also alumni of this department. He is currently serving as the Vice Chancellor of the KTU, Kerala Technological University. I just figured only a few number among the former alumni of this department. I think the one of the departments in Cochin University which is getting more alumni support is ship technology. And recently, with the initiative of the Professor Shivaprasad and Professor Dr. Sadish Babu, uh, uh, actually yielded fruitful results for generating funds for the development of this department from the Cochin Shipyard Limited and the Masagon Dock of Mumbai. Probably Dr. Sadish Babu will tell more about that. We could have to get a funding of 2.5 crores from the Masagon dock. Apart, that's only actually that process is initiated by the Professor Shivaprasad and Dr. Sadish Babu. Of course, our department is also having a generous funding for the research-oriented CSR funding from the Cochin Shipyard Limited. And I am a little bit sad today because one of my close friend, Professor Shivaprasad, because he is always an encouraging spirit and encouraging support for all the activities what I used to do in Cochin University, because he used to guide me and he used to discuss with me, as I mentioned earlier, with respect to tapping the CSR fund from the different companies related to the shipping industry. He only directed me, you just contact there and you just visit there, and like that he actually initiated me and advised me the possibilities for exploring the more research collaborations and more what I can tell you, getting the CSR fund for the development and building the infrastructure for the department as well as for the university. I hope he will also continue. Even he is superannuating from the service of the Cochin University of Science and Technology on this month, 13th of this month. I hope he will guide us in future also, and I hope he will be with us in all our activities in future. Even though this retirement is we cannot avoid it, is I wish him a very happy and successful, active retirement life, and with more academic collaboration with all the institutes. Professor Shivaprasad is, I need not have to mention much more introduction about him. He is a member of the several committees in India. He joined in the ship technology department in the year of 1994. It's about 32 years of 1994, 32 years back. So he has that much years of service in Cochin University. I think he joined maybe as a student of this department, maybe much more earlier. So he maybe have more experience with it rather than anybody present here. And he served several committees related to the maritime bodies of the India in national level and international level. And he's also he was also a director board member of the prestigious Bharat Heavy Electrical Limited's BHEL. So he served so many, served as a member of so many such regulatory bodies and administrative bodies and all those things. Of course, his service to the nation is an asset. Anyway, I hope once again I request him to render his all support for our future activities. So that's why, with all of your permission, I'm not taking much more time for discussion because you have to take more time. With all of your permission, I would like to officially declare that this biennial conference, third international conference on advances in naval and ocean engineering, is officially inaugurated. Thank you all.
Thank you, sir, for your kind words. Now it is time to invite our honorable chief guest of the day, Mr. Yoichiga. He is regional manager of Class NK Middle East and South Asia stationed in Dubai. He graduated with a master's in structural engineering from Hiroshima University and joined Class NK in 1992. He began his career in the Rural Development Department and has since worked in various capacities, including the damage investigation and feedback section and local survey offices in Japan, Singapore, and Germany. Just before moving to the Middle East, he served as a GM of the survey department at the Tokyo head office, where he controlled and supervised Class NK's survey activities worldwide. He was now appointed as regional manager for the Middle East and South Asia in April 2022. Now invite Mr. Yoshiiga to release the conference proceedings and request the distinguished guests on the dais to receive the first copy. Please say a few words, sir. I humbly invite Mr. Yoshiga to say some few words.
Respected Chief Patron, Professor Junaid Bushiri, and respected Chairman, Professor Matyalgam A, and respected honoring Professor K. Shivaprasad, respected faculty members, students, friends, and ladies and gentlemen, a very good morning. It is an honor to participate in the inaugural ceremony of the prestigious iCANOE 2025 conference. Events like these offer an excellent platform for students and research scholars to showcase their work and share insights into their research. Hosting such conferences at universities is especially beneficial, as it allows undergraduate students to gain exposure to a wide range of topics and learn from distinguished speakers. This experience can serve as a powerful source of inspiration, helping them shape their academic and professional journeys. The theme of the conference is very relevant, as digitalization and decarbonization are shaping the future of the shipping industry. Digitalization has made it possible for ships to transmit data continuously to companies without human intervention. This data is being analyzed to optimize ship operations and enhance efficiency. Notable advancements such as digital twins and artificial intelligence are key outcomes of this transformation. And these technologies are paving the way for the automation of most shipboard operations with the goal of minimizing human error. On the other hand, there remains considerable uncertainty regarding the most viable alternative fuel for new building projects. Many of the technologies associated with these fuels are still in development, making it difficult to predict their future trajectory. Adding to this, uncertainty is the recent setback in adopting the IMO's midterm GHG measures during the extraordinary MEPC session held in October this year. Despite these challenges, the maritime industry must continue to adapt to emerging technologies and initiatives to ensure long-term sustainability. India has consistently been at the forefront of research and innovation. Indian postgraduate and doctoral students are making their mark at leading institutions across the globe. These research efforts have also contributed to significant national achievements, such as the construction of the indigenous aircraft carrier at the Cochin shipyard and the development of various homegrown technologies. For CUSAT, research plays a vital role as it formed the foundation for rural development. The organization actively engages in pioneering joint research projects with the maritime industry in Japan, focusing on cutting-edge areas such as autonomous ships and zero-emission vessels powered by alternative fuels. The Department of Ship Technology at CUSAT and CUSAT share a long-standing and mutually beneficial relationship. For over 15 years, CUSAT has been recruiting naval architecture students graduating from the department, many of whom have gone on to excel in their professional roles. Their success is a testament not only to their dedication and hard work, but also to the high standard of education provided at CUSAT. To further encourage research among undergraduate students, CUSAT has instituted the NK Awards, which recognize the 3 best student projects each year. These awards will be presented during this inaugural session. I would like to take this opportunity to commend the organizers and faculty of the Department of Ship Technology at CUSAT for their dedicated efforts in making this conference a reality. I hope the delegates find the presentations engaging and can take away valuable ideas and insights that inspire further exploration and innovation. Now, let us celebrate the power of knowledge and the spirit of innovation. Thank you.
Thank you, sir. Your presence have truly elevated the spirit of this event. Now, let's invite Mr. Sumitan Sambat, who is currently the General Manager at CUSAT. He brings with him vast experience from previous roles at Tempo Shipbuilding and Engineering Private Limited and ABG Shipyard Limited. Mr. Sambat holds a BTech in Naval Architecture from Indian Institute of Technology, Kharagpur. We humbly invite Sumitan sir to the podium to present his felicitations to the gathering.
Yeah. Honorable Vice Chancellor of CUSAT, Dr. Junaid Bushri, Dr. Madhiyaragan, Head of the Department, Mr. Yoshi Igasan, Class NK Regional Manager, Dr. K. Shivaprasad, Vice Chancellor KTU, faculty members, students, industry experts, ladies and gentlemen, I wish you all a very good morning. At the outset, I am delighted to be here once again, and it's a true privilege for me to join you for iCANOE 2025. This conference serves as a distinguished platform that brings together innovators, thought leaders, and experienced industry experts from the maritime domain. On behalf of Class NK, I extend my sincere congratulations to Cochin University for organizing this conference. This gathering comes at a very pivotal time when the Indian government has focused its policies for the growth of the maritime and shipbuilding industry. Historically, India for many centuries has been a very strong shipbuilding nation, but over the last few decades, this advantage has been lost temporarily. But I'm sure with this present policy thrust of the Indian government, India is poised to regain its position as a leading shipbuilding nation. The department and its students have a crucial role to play in shaping a sustainable and technologically advanced future for the Indian maritime industry. Class NK has consistently been at the forefront of innovation, delivering cutting-edge solutions and contributing to global maritime society and sustainability. I would also like to emphasize that Class NK's technical information, rules, guidelines, and latest information is available on our website. And this is can be accessed by any of you. It's free of cost, and all you have to do is just a registration, formal registration is necessary. And I would encourage all of you to utilize this information for your projects. And I'm sure this will help you in, being in touch with the latest information. I'm confident that the next 2 days will foster very meaningful discussions and collaborations, which will definitely be useful to all of us in the industry. With that, I would like to conclude my felicitations. Thank you.
Thank you, sir. We are deeply honored by the presence of our distinguished dignitaries. As a gesture of our sincere appreciation, we would like to present a token of gratitude. I now request our respected head of department, Dr. A. Madhyaragan, to kindly come forward and present the mementos. I request Professor Dr. Junaid Bushiri, Vice Chancellor of CUSAT, to kindly come forward and receive our token of gratitude. I now request Professor Dr. Junaid Bushiri, Vice Chancellor of CUSAT, to kindly come forward and receive our token of gratitude. I now request the respected Mr. Yoshi Iga to kindly come forward and receive the memento. Now, I request Mr. Sumitan Sambat to kindly come forward to receive the memento from the head of department. Thank you all. Kindly please come back to your seats. Dr. Shivaprasad K is a highly accomplished professor in the Department of Ship Technology at CUSAT, currently serving on deputation as the Vice Chancellor of APJ Abdul Kalam Technological University. After 32 years of dedicated service, he is retiring from the department. I invite Professor Dr. Satish Babu PK, Associate Professor, Department of Ship Technology, to felicitate him.
A warm good morning to one and all. Respected dignitaries on the stage, off the stage, conference delegates, my friends, naval officers, students, and everyone present here. I'm very happy that the third edition of iCANOE has been formally inaugurated just a short while ago. After the resounding success of our first edition in 2021, we have decided that we will have this event every 2 years. So here we are standing with the third edition, and I wish this conference all the very best. iCANOE is not just a place to just present research papers. It is a place we greet and meet our friends in the industry and provide a platform for the industry academia collaborations. The contribution of the department in the maritime sector is unparalleled. As it was already mentioned, many of our alumni are now holding leadership positions at various national and international levels. We are also getting significant support from the industry. As Honorable Vice Chancellor has mentioned, we have got 2 major CSR support, one from Cochin Shipyard to establish a center of excellence in sustainable shipbuilding technology in our department. Our vision is to have an international standard center here, which will act as a hub for cutting-edge research. We will have high-end workstations, latest ship design softwares. We are going to have in-house design, and we are also going to invite proposals from outside, and we are going to appoint a professor of practice to steer this. And it is going to be for 3 years. And we are expecting that the support will continue in the near future. Another one is, we know that department building is getting very old. So me and Honorable Vice Chancellor visited Mazagon Dock Limited. We called on the chairman and managing director, and we presented our case. And immediately, without any hesitation, he has granted another major CSR funding to make academic blocks for the department just outside our library. So I take this opportunity to thank both organizations for their generous support for the department. We have just celebrated our Golden Jubilee last year, and as the policy of the government is to have maritime sector as a strategic sector, I'm sure that the coming years will be very challenging as well as more enlightening for our students and our graduates. With this, I wish the conference all the very best, and I move on to my assigned task, that is to say a few words about Dr. K. Shivaprasad, who is going to retire at end of this month, and he has decided not to take the superannuation. So I think it is a very big loss to the department, and he has served 32 long years. I can say he has carried the department on his shoulders all these years, and he left. He could have got a number of many opportunities in the industry. He was appointed in the Mazagon Dock Department, shipbuilding yard, and he took a master's from USA or UK, so USA, UK, sorry. And he came back to the department, And when I joined the department, he was in the final year. So that way he was a super senior. He's the first naval architect to become vice chancellor. So there are many firsts in his case. Naval architects are known for their expertise in ship design and ship building, but he decided to take a different route and become an expert in ship breaking and ship recycling. And he did his PhD in that field. He has contributed in different areas, including the inland water transportation in Kerala. He has been in number of committees and he has surveyed so many boats, especially after the Tekadi incident. The government of Kerala has decided to have they have empaneled professors, and he has visited the length and breadth of our state and certified many boats. And apart from being an academician, he has been an excellent research guide. He was a mentor to many of us. He was a good writer. He was a poet, and he was also an able administrator. He has authored a book on 50 glorious years of shipbuilding or ship technology, and it was released last year. And I'm sure it will be a good reference material for all the future naval architects who would like to know how this department has progressed from scratch to this level. In the department, he has performed all roles, starting from head of the department to coordinators of SNAS, internship, placement, alumni hours for several years. I remember once he told me that he has made 15 question paper in one semester. So you can imagine the kind of workload he was taking here. He took a special interest in developing department infrastructure. With the help of Class NK, he has made a drawing hall. Even that main gate, he came with his initiative. He has developed a model making lab with the Cochin Shipyard Limited, just to mention some few examples. His involvement in the department was so complete. He knows each and every alumni of the department, his name, his batch number, and where he is working. It is very difficult to have such association with the department. His influence extends beyond academia. As it was mentioned, he was member of a large number of committees. He was a member of board of directors for Bharat Heavy Electricals Limited, Bureau of Indian Standards. He has done number of industrial consultancy works and sponsored research. And he has participated in various technical committee members. Incidentally, he is also a member of the India Technical Committee of Class NK Japan and National Monitoring Committee for Minority Educations. Well, I don't want to take much time. I can go on and on to speak about him. But on behalf of everyone present here, sir, we would like to thank you for your outstanding contributions to the department and the university. Thank you very much. Let me also congratulate all the award winners for your achievement. Thank you very much.
Thank you, Satish sir, for the felicitation. As a token of respect and gratitude from us, I humbly request our VC, Professor Dr. Junaid Bushri, to honor Professor Dr. Shiva Prasad Ki. I now invite Shiva Professor to please share a few words with us about his experience with the department and the university.
Very warm good morning to those who have assembled here for the inaugural session of the third edition of iCANOE 25. Respected Chairman of the function, President of the function, Dr. A. Mathiyagan, respected Honorable Vice Chancellor of Cochin University of Science and Technology, Dr. Junaid Bushari, Chief Guest of the function, Yoichi Iga-san, Regional Manager of Middle East and South Asia of Class NK, Japan, Mr. Sumitran Sampath, General Manager of Class NK, Dr. Satish Babu, Associate Professor, and presently the Director of Kunyali Marikar Marine Engineering College, Dr. Rajesh Nair, Dr. Hasina, my respected teacher, Dr. Krishan Gutti, Officer in Charge, Naval Construction Wing, Commander Deepak Sebastian, Dr. Senthil Prakash, Dean of Engineering, Cochin University of Science and Technology, my dear colleagues, dear students, alumni members, delegates, and others. I will not stretch my speech because you are all waiting for the other important function which is going to happen, the prize distribution of Class NK Best Project Award. I also, at the outset, I congratulate the winners. I can see two winners, but the third winner I don't know whether he has come or not. Congratulations. I started my journey in Department of Ship Technology officially, academically in 1984 when I joined here as a BTech student of the 10th batch. But the story slightly goes beyond that, before that, because as a schoolboy, I reside very nearby, some 500 meters from the campus. I stayed there. I used to stay. So as a schoolboy, I used to visit the university because this was all open for all. One of my ex-students used to say, "Sir, I have seen only one open university in the world, that is Cochin University of Science and Technology." His understanding on English was slightly less. What he meant was, this is the only university where the entire university in India is open to all. No walls to protect. But very interestingly, we have departments inside with protection walls. This is the only open university. For him, it was only one open university in the entire world. So I used to, as a schoolboy, I used to come to the ground, university ground, and I used to play cricket there. So during those days, cricket was not a very popular sport in India. And most of the students then joined in this department had no prior knowledge and experience with cricket. So the students of Cochin University of Science and Technology, Department of Ship Technology, I used to coach them in cricket right from 1980. So my connection with Department of Ship Technology starts from 1980 and it continues still. After probably 45 years, I'm still with the department. I can also point Dr. Krishan Gutti, who joined in 1976 as a BTech student. He still continues his association with Department of Ship Technology, very active and kicking. This is the culture of Department of Ship Technology. The alumni members of this department, they never go out of the association. It is a real alumni association. You can probably give us an example of best alumni association in the world. And the entire infrastructure development, probably after
1990 was done by the contribution from the Department of Ship Technology alumni members. Even this particular hall, conference hall, was fully furnished with the support of Department of Ship Technology Alumni Association. And you can see the name. We are dedicating this one to the Department of Ship Technology Alumni Association. And one more example of the activeness of the department is the currently running live and active memorandum of understanding with industry. Usually, MOUs will be signed and will be on paper and never it will be in action. But our MOU with Class NK, it started 2006, probably 20 years before, is still very active. That is why the regional manager, the regional head of Class NK, Mr. Igasan, is here for this function. That shows the closeness, the association, live association with the industry. We have very good association with Cochin Shipyard also, and we survived because of that association. And also Indian Navy, we have an active, not an MOU, official MOU. We have an agreement. That is why we are surviving now. And the future, you have to think about the future of Department of Ship Technology. If you want to sustain, there should be big involvement and there should be a big support from the university. Otherwise, there is a potential problem that you can probably see. It's very obvious. So if I say about the characteristics of the department and my association with the department, it may go probably hours together. So I don't want to extend this because you're all waiting for the next program to happen. So I don't feel like retiring because I stay nearby. I stay probably adjacent to the university, very near to the campus wall. So I don't feel like retiring. I will be here with you for whatever help that you want. And if I have that particular capacity and I have that time to give some support, definitely I'll be there with you. With these words, I again wish this conference a big success. And also I congratulate the Class NK Best Project Award winners. Thank you very much.
Thank you, sir. Now I request Assistant Professor Dr. Rajesh P. Nair, convener of the event, to deliver the vote of thanks.
Respected President of this event, Dr. Madhyaragan sir, our beloved Vice Chancellor Junaid Bushri sir, Chief Guest Sri Yochiga, our Professor Shivaprasad sir, then senior professors, my dear colleagues and my dear students and other participants of iCANOE. We as our Bushri sir mentioned, this is an event happening every 2 years. So in between these 2 years, we have another event which is called DIMS, that is being organized by alumni, Ship Technology Alumni, DOSTA's International Maritime Seminar. So every year, Ship Technology will conduct one conference. So it started in 2000, iCANOE started in 2001 with Satish Babu sir as the convener. And being the success of the first conference, we thought we can conduct it in every year. And last iCANOE 23 was also a grand success. And this year also, we could able to do all these things in spite of tight schedules, like the semester endings and other happenings. And we are glad to have the chief guest Yochi Iga sir with us. Let me come to my duty. Let's thank the chief guest of the day, Yochi Iga sir, for being facilitating this function. Thank you very much, sir. And our beloved Vice Chancellor Bushi sir inaugurated this function by releasing the conference proceedings. And thank you, Bushi sir, for coming for this function and inaugurating this function. And all this happens because our HOD sir, Madhyaram sir, give us, myself and Hasina teacher, the chance to coordinate this function. And I take this opportunity to thank the President Madhyaram sir. And the felicitation was conducted by Sumit sir. Thank you, sir, for coming for this function. And the Sadish Babu sir, sir is the, I used to tell iCANOE is a baby of Sadish sir because he only initiated iCANOE and we are just continuing. Thank you, Sadish. And the star of the day, our Shiv Prasad sir, as Vice Chancellor Bushi sir mentioned, sir is retiring on November 30th. But still, his relations and his connection with our department never ends. So I take this opportunity to thank Shiv Prasad sir for coming for this function. And the Class NK award winners, first, second, and third best project award winners, including Atul Kunjumon, and other students. And also we have another function that's happening tomorrow. That is Captain Mohan Ram Endowment Award for the best Navy student. So I thank that winners also for coming for this function and making this iCANOE a successful one. And thank you participants for coming for this function. Without you, this conference is incomplete in all sense. So I thank all the all representing participants as well as the other participants coming for this function. Thank you very much. And also our colleagues, Manoj sir, then our Aravind, then I forgot to tell Dean sir, Senthil sir, and Krishnagurti sir, Ebenezer sir, for coming for this function. Actually, Ebenezer sir and Krishnagurti sir is delivering the keynote address for this 2-day sessions. Thank you very much for coming for this function. And our last year convener, Paul sir is here. Thank you, sir, for coming for this function and chairing a session. And of course, the students, which starts with research scholars, MTech students, and BTech students, because they were actually our hands. We have some ideas, but once it comes to the real end, it is happening because of you all. Like all these posters and proceedings, printings, certificates, receipts, and whatnot. Everything, like a conference, these tags and all happen because of you. And thank you, students, for making this wonderful coordination. And I wish all the students to attend the sessions also and get some enlightenment and some insights from this attending this conference. Thank you all. Thank you very much.
Thank you, sir. With this, we conclude our inaugural session. Once again, the Department of Ship Technology extends a warm welcome to everyone attending this 2-day conference. We will resume with the Class and Key Award ceremony at 11:30 a.m., followed by the scheduled sessions. Meanwhile, please feel free to enjoy the tea arranged at the entrance, and we will have a group photo there. Thank you.
Privileged to announce the winners of the Class NK Award for the BTech year 2025. Good morning, respected guest, head of department, officer in charge, Naval Construction Wing, faculty, guest, and ladies and gentlemen. Class NK stands as one of the world's most trusted classification society, known for its integrity, precision, and commitment to safety at sea. Through rigorous standard, innovation research, and global technique support, Class NK continues to shape a safer, cleaner, and more efficient maritime industry. Their seal on a vessel reflects excellence, reliability, and confidence across ocean. Every year, 3 students from BTech course from Department of Ship Technology are chosen and awarded by Class NK for showing high level of ingenuity and innovation in the final year BTech project. For the year 2025, the third prize in Best Project has been won by Atul Kanjuman for designing a 1500-meter cube factory stern trawler. Atul presented a comprehensive design of an offshore commissioning and service operation vessel for wind farm maintenance. His project combines advanced hull development and CFD-based performance validation with rim drive azimuth propulsion and dynamic positioning for high-precision offshore operations. With a methanol-ready machinery concept, the design reflects a strong commitment to sustainable offshore energy support systems. I request the Head of Department, Professor Mutyagazan, to please felicitate the award. Thank you, Atul. I would request you to please pay your gratitude and come on the dais for the same.
So good morning to all. So respected delegates on the dais. So the delegates from class and game, my teachers, my friends and all gathered here. I am with so much joy and pleasure that I've received this second runner-up in this prestigious class and game Best Project Award for the year 2025 for my BTech final year project. So first and foremost, I bow my head in front of my Almighty, because without without their blessings and all, I would not be here. So I extend my heartfelt thanks to my thanks to Class and for organizing this prestigious award, for encouraging and encouraging the innovative ideas from students like us, for giving this actually giving this final year project awards for Class and game. So I'm deeply thankful to Department of Ship Technology, which was not actually an institution for me. It was like it was living a life within these 4 years in this department, and it actually nurtured me, it shaped me, and everything. And I'm deeply thankful for this Department of Ship Technology. And a very special note of gratitude to my project guide, Dr. Sadish Babu PK sir. Without his support and all, I could not be here. And my project's backbone was the guide from this department and CSL also, Cochin Shipyard Limited also. So I am also thankful to the external guides from this Cochin Shipyard Limited, Mr. Harikrishna sir and Sahit sir. Their knowledge and their insights, the insights were very much helpful for me to attain this BTech project awards. So I'm sincerely thankful to Cochin Shipyard Limited for that. I gratefully acknowledge the help and encouragement I got from my seniors and juniors there. Their support was very much actually helpful for me to complete this project. From seniors also and also from juniors, their moral support and all was very much helpful. So I thank these juniors and my seniors for this support. And at last, my friends from batch 46. and they have been my entire support throughout this final year for completing my project and some problems, and also they were very much helpful for me to attain this award. So I am deeply thankful to my family and my friends. As many of you know, my vessel was a commissioning service operation vessel. So it is actually first of its kind from this department, and it was a Herculean task for me to complete this project, because this CSOV is actually always a new word for everyone who is listening to what is CSOV, how to do CSOV, and that is also a challenge for me to complete the task. And the support and this guidance I have got from this department and CSL helped me to achieve this, and helped me to complete this project. And hopefully I'm here, like I got second runner up, and that's it. Thank you.
Thank you, Atul. The next felicitation is for Sub-Lieutenant Shailinder Singh, whose project addresses coastal logistics through a 4300 deadweight salt carrier powered by innovative suction wind sails. His design integrates aerodynamic optimization, hybrid propulsion, and shallow draft RSV compliance to offer a fuel-efficient and commercially viable green shipping solution for Kandla-Dahej trade route. The project showcased true innovation in wind-assisted coastal transport. I request Subramanian Shailendra Singh. I would request Professor Shiv Prasad to please present the award. I now request Subramanian Shailendra Singh to please convey his vote of thanks.
Good morning to each and everyone present over here. Respected Head of Department, Dr. Madhyagan sir, all the dignitaries from Class NK Society, Commander Deepak Sebastian, OIC Naval Construction Wing, professors, and all the young minds who are sitting over here. It's a moment of great pride, and it's a gratitude for me that I'm standing over here and receiving this best award for the vessel which I have designed, that is 4,300 deadweight coastal bulk carrier. I express my heartfelt thanks to Class NK Society for selecting this project, as it is a very big honor for me. Also, I would like to extend my sincere gratitude to my project guide, who is also sitting over here, Dr. Krishnagurti sir. Sir is very helpful, and at each and every moment of time, even after having busy schedule, whenever I used to call sir, sir is always there in the department for helping me. Sir was a person who always pushed me to do some innovations in my project, to carry out the NC simulations, to tell and telling me that what other things I can do, which will be different from the other works which people will be doing here. So that was a very helpful. I was very great. It was a great moment for me that I got Krishnagurti sir as my project guide, and so is the same for all the other persons also. Sir motivated me to adopt this suction sail technology, which is a new innovation which has not been accepted in many of the countries till now. I think that only 7 to 8 vessels are there worldwide, and now people are accepting it. So it is a type, just as a brief introduction I want to give, that it is same as the rigid sails, but it makes use of the Quanda effect to eliminate the boundary layer separation, and we can delay the boundary layer separation, giving us more thrust. As you all know that in the coastal regions of Gujarat, there is a great significant wind power which we can generate from there, and the vessel is intended to work on that principle. It's a hybrid vessel. It makes use of the diesel propulsion also, and in good wind conditions, it can get propelled by the this wind suction sails also. I also thank my external project guide, Mr. Hari Krishnan sir and Sahid sir, who are there from Cochin Shipyard Limited. Sir helped me, mentored me, and because of sir's great knowledge in softwares like NAPA, NavCAD, ANSYS, it was possible to do everything and complete my project. Even it was a very busy schedule for sir in CSL, but the faculty in CSL and the people working in CSL, they are very much helpful. I thank my project coordinator, Lieutenant Commander Anand S. Nair, who was my deputy IC, and sir helped me to complete my project on the given timeline. I also want to thank my department for providing me the environment which I am blessed with, and above all, the trust to explore the new ideas also. I want to mention the special thanks to my professors, Dr. D.D. Ebenzer and Manoj T. Isaac sir. Because of continuous efforts when I was working on to resistance and propulsion, I learned the extra things which I might have missed during my third year and second years of studies. I thank entire NCW team, of which I am also a proud member of. They gave me this opportunity to work on such a type of project. Finally, I would like to thank all of my fellow juniors and course mates who always supported me at each and every point of time. Also, I want to give you a kind of, I want to tell you all guys that whosoever is working on their final year project, it's a best opportunity when you can put on the things which you have learned from that last 3 years. You can find out that how much it is helpful, and you can check on to your knowledge to look onto the things again. So I want to tell you that please take it seriously. This is a time when the knowledge which you are gaining from the books, you can really explore it and you can put it into the practical problem solving. And with this, I conclude myself. Thank you. Jai Hind, Shamno Varna.
Very well spoken. Now for the winner of the Class NK Best Project Award. The winner for the Class NK Best Project is Andus Geo for excellent project for an excellent project that envisioned a battery electric RoPax ferry designed specifically for the sensitive waters of the Andaman and Nicobar Islands. His work presented a zero emission vessel capable of carrying 250 passengers and good amount of vehicles, and introduced an innovative stern tunnel propulsion arrangement to significantly boost efficiency. The project stood out for aligning modern naval architecture with India's clean maritime vision. I would request Dr. Krishna Kutti to please hand over this award. I now request Andrew Gio on the dais to present his vote of thanks.
Good morning, all. Respected Chief Guest, Mr. Yoichi Iga, Regional Manager of Middle East and South Asia Class NK. Mr. Sumitran Samant, General Manager, India. HOD, Mr. Madhyagan Sir, and all the respected professors, industry experts, and my dear friends. Today is one of the most proudest moments of my life. Receiving the Class NK Award for the best BTech project is an honor beyond my words. I would really like to sincerely thank Class NK for realizing the student research that are happening here and inspiring young naval architects like me. Thank you, Class NK. Now, I would like to give a small detail on my project. My project titled MV Samudra is a battery electric inter-island RoPax ferry, accommodating 250 passengers and 15 cars or 3 buses. It's operated in the inter-islands of Andaman and Nicobar Islands, starting its journey from Port Blair, then to Havelock Jetty, then to Neil Jetty, then returning back to Port Blair. The speed of the vessel was 12 knots, and the innovation that I used in my vessel was a stern tunnel design, which I got the resources. There was a design study of a Samoa ferry made by Japan International Conference Agency, from where I got the idea of the stern tunnel, from which I incorporated in my vessel, which increased the propeller diameter of my vessel by 1.1 times of its draft, which increased its propeller efficiency by 20%, and the overall efficiency of the vessel was increased. And the other innovation was the battery electric hybrid propulsion system, which operated using a battery and a diesel generator to reduce the emissions. The main innovation I need to use this stern tunnel was because of the low draft that was present in the Nile jetty. Now, I would like to use this moment to thank everyone who helped, all people and the organization who helped me achieve this great success. Thank you all. Now, I would like to say some words to the organization. My project was lucky enough to be collaborated with Cochin Shipyard Limited, from where I got the resources, and I would like to especially thank them for trusting me with a task which needed to go beyond theoretical studies and go into real world industry experience. Now, I would like to thank specifically CSL for helping me to give access to software such as NAPA and NavCAD, without which the scope and the accuracy of the project would have been difficult to achieve. Now, to my mentors. Firstly, I would like to thank Professor Dr. Shiva Prasad sir, my project guide, who always helped me in my project, even though in his busy schedule, he always maintained to take time for me to help me throughout the project. I am always thankful for you, sir. Now, I would like to thank the CSL, Cochin Shipyard Limited faculties, especially Hari Krishnan sir, Senior Manager, Basic Design, and Said sir, Assistant Manager, Basic Design, who were there throughout my project from start to end. Whenever I was stuck or unsure how to proceed, they always helped me with their critical strategies and ideas, which helped me to plan ahead of time. Thank you, Cochin Shipyard Limited, for being such a big part in my project. Now I would like to thank my family, friends, juniors, and seniors who were always there with me, providing constant emotional support, whether in case of doubts or anything. They always help me. Thank you to you all. Now, last but not least, I would like to thank the support staff and the entire Department of Ship Technology for providing a environment where this project could be done. I am humble enough to receive this recognition, and I carry forward to commit the innovation and integrity towards my career. Thank you all.
Thank you, Andrews. And undoubtedly, it's a proud moment for all of us. And to capture this moment, I now request all the award winners and the panel members to please come together for group photographs.
Congratulations to all prize winners. Thank you, Shashwat. Now, let us move on to the first keynote session. The keynote speaker for the session is Professor Dr. P. Krishnakutty. He is an emeritus professor in the Department of Ship Technology and is highly regarded for his expertise in ship hydrodynamics, maneuvering, and ocean wave structure interaction. His distinguished career includes senior faculty positions at CUSAT and IIT Madras, culminating in a senior professor role. He holds advanced degrees and completed most postdoctoral research at Glasgow University, UK, cementing his status as a leading authority in marine science. I invite Krishnakutty sir to deliver the keynote speech.
Yeah, very good. Good afternoon. I think it's past third or it's morning now. To all of you, all the participants of the presenters in the conference. So the topic of my talk is on the yeah, the topic is going to be on ship hydrodynamics. Primarily when the ship operates in restricted waterways, in shallow water. Restricted waterways means in shallow water, and also in canals, widthwise restriction. Shallow water means depthwise restriction. The ship is going to experience a deterioration in the hydrodynamic performance when it enters from deep to shallow water. So what all things it's going to happen to the ship while it's transferring from deep to shallow water? The shallow water operations usually the ship encounter is when it's entering from deep sea to the harbor area where the water way is restricted, and also the ship operates in the proximity of other ships or structures, which induces a lot of hydrodynamic flow characteristic change around the ship, resulting its negatively influencing its performance in such an environment. So we'll just touch upon that. And another area where you have to look into is the inland water transport. Waterways are restricted in the widthwise restriction and also in the depthwise restriction, depthwise way, the depthwise. So what all things which would happen to the vessel when it operates in the restricted waterways? So not working. Yeah. Okay. So say as I said, it's a confined waters. It's shallow and restricted waterways, which usually, as I mentioned, harbor, canal, and all that. And ship operates in crowded area, whereas it's adjacent ships or the waterway boundaries, particularly inland waterways. You have the maybe the wall boundary, canal boundary, or the river bank, which is going to influence the operation of the ship, changing its hydrodynamics. All these things lead to a deterioration in its operability, primarily due to the flow variations around it. So there is a possibility of hydrodynamic interaction. That is when two bodies come together. We'll see subsequently. So how the ship operating is going to influence another ship, how the particular ship which is being operated, how it's getting influenced. If it's a moored ship, what's happening to the moored ship. If it's there's a port structure, how it's going to influence all this, going to have a practical relevance and will have a adverse effect on its performance. So that's the next point I said, it's a rope failure for moored ship. The ship also is subject to a phenomenon called squat, which is a combination of a trim and sinkage occurring to the ship when it operates mainly in shallow water. And along with shallow water, if the waterway is restricted, then you have a more pronounced effect of these things. And also, the ship becomes sluggish in the sense that its response to the rudder become, bad, and so it may become difficult to turn the ship, or change the course of the ship. Then, because when the ship enters to the shallow water region, you can see that there will be increase in resistance, and this increase in resistance leads to involuntary reduction in speed of the ship. Automatically, even if the captain of the ship is not reducing the speed, the ship involuntarily itself get the speed reduced due to the increased resistance. So, and also the wave, the ship generated waves will build up in shallow water. And as you know that particularly long waves, if it's creating, then the buildup is more towards the shore area, which if you recall the tsunami, which has happened in, I think, 2004, December. So the wave was pretty long underwater, earthquake, which created it. The period is very long. The waves were not felt in the mid-sea by the ships which were crossing but it built up at the shore where I think it has gone up to 12-meter height. So that buildup will happen. This concentration of energy will transform the wave. So here also for the ships which operates in shallow water primarily, the waves will build up towards the shore. And particularly when it comes to the beach users or the small pleasure crafts which are being used in the beach side will be subject to dangerous position. So all this build up. So these are the major transformations which occur to a ship when it enters from deep to shallow water. There are many things. Resistance increases, maneuverability reduces, wave generated effects leading to transformation and all the buildup. Then the adjacent vessels, how it's getting influenced due to hydrodynamic interaction. Then if it's passing through a harbor, the moored ship is there. What happens to the moored ship? The moored ship will have, it's moored with the ropes and all that. Obviously, there are these interactive forces, that is, ship is moored stationary, and there's another ship passing by close to it. This can induce a high load on the mooring line. There are many incidents, the mooring line snapped and the ship becomes stranded, the moored ship. So these are the incidents which happen, so collisions. So there are many things which happens during the, when the vessel operates in restricted waterways. So just looking to the hydrodynamic interaction, I'm just taking one by one. Just looking to the interaction, that is when two ships meet or pass by, what happens to that? The ships will have particularly when the ships are close by, and there are many factors which determine the interactive force between the two ships. How the proximity of the two ships, that's the separation distance, Then comes the speed at which it is operating. Then comes what is the size of the ship, relative size of the two vessels matters. What is the underwater form of the vessel? If it's whether it's a tanker vessel or it's a container ship, all this will influence the hydrodynamic interaction forces. So that is what is being mentioned here: closeness and proximity, and yeah. So effect on the mode ship, as I mentioned. Controlling the ship in shallow water is rather difficult because ship is controlled, the direction of the ship is controlled by the rudder. Rudder become effective when the flow to the rudder is more, because that the lift is proportional to u square, velocity square of the flow. So if the flow to the propeller, to the rudder reduces due to the shallow water effect, then naturally the rudder effectiveness is low. That's why you may find that inland vessels, the rudder size is comparatively large than the seagoing ships. So that is the reason. And also you may see that big ships, when they come to the port, they are not running on their own. They are assisted by tugs because it's difficult to generate the control forces adequate to take it to the key, so to the berth. So all this comes into, so there's such high chance of collision. Then depending on the size, forces acting on that. So the design of the mooring systems and fender systems need to consider the hydrodynamic interactions imparted by a passing ship in such situations. Yeah, these are things I've covered. Boat ship along the case I've just said. So this can happen to even anchor ships. So there's a ship passing by. It can, the anchors can be pulled out because of the interaction effect. Then usually there are two ways of, the ships operating, both ships moving in the same direction. That is one ship overtaking the other one. We usually call overtaking maneuver. Or there one ship coming in the opposite direction, we call it a meeting maneuver. So it's so these two situations, the flow characteristics changes. So accordingly, you have to look to the relative flow velocity between the two vessels, which will where the velocity of flow is more, naturally the pressure drops. Bernoulli's equation, where isn't it? That's what happens when the velocity increases. So when the pressure drops, the two vessels try to attract each other. There's a chance of collision. So that's what is going to happen. That is in the breadthwise direction. Then along with you have the yaw moment, which also can make the ship turn and go and hit with the other ship. Another operation is replenishment, very common in with naval ships, where the naval ships need to be replenished with its consumables, oil or other, mainly oil. And so naturally, when the two ships operate, they operate very close by. So hydrodynamic interaction is very strong between them. And but they do it while moving, not in a stationary condition. Both the ships move in a synchronous way so that the controls become effective. That is, even if there is a deviation, it can be compensated with the rudder because there is a flow. But if you put it stationary, rudder become ineffective. Okay, this is just an indication of that. These pictures I've taken from internet. So these are how the forces act. This is a encounter maneuver or meeting maneuver you call. So this is the ships in the opposite direction. And how the pressure is going to vary. This positive means high pressure and this negative pressure means low pressure. You can see that the attraction chances, that is the forces said that both get attracted to each other and there's a chance of collision. All this I've said depends on the speed of the vessel with which it operates. That's a relative speed is important. Then size of the vessel, separation between the two vessels. All this matters in the generation of the interaction forces between them. Then also the underkeel clearance, how much water is there, that is how shallow the water is. If it is very less, the effect will be magnified. So then rudder size and response time. So what is the size of the rudder, which determines the control force and moment generation. So if the rudder area is less, then these forces and maneuvering become difficult. These are some of the results which I've this, as I mentioned here, as I was with Glasgow University for some time. So this is a project sponsored by European Union to study the hydrodynamic interaction. This happened about more than 20 years back. I just picked some results from the report. So this is the encounter maneuver, how the forces and moment, mainly the two components we consider as the sway force, that is the Y force, and the yaw moment, which is a moment about the vertical axis of the vessel. So you can see how they're varying. So this is the against the staggered distance, that is the so distance in the lengthwise direction. So and also different water depth. And you can see the outer one, this is interaction force. If the ship is, abreast, then the staggered distance is 0. So this is what is shown here. You can see that interaction force, the negative one is the attractive force and positive one is the repulsive force, basically. So we can see that when the water depth, this is for the deep water condition, this is water depth, I think it's H/2, and this one is for very shallow itself. So when the water depth decreases, you can see the hydrodynamic force, how it's going to vary. So that means the higher the shallow water, the hydrodynamic interaction, the forces become very high. This is another with respect to the spacing, that is how they are separated. This is a case where both ships move in the same direction, and this overtaking maneuver. You can see some of the results coming out of that. I'm just skipping through that. This only just to show that how the forces vary with respect to water depth and also with the separation distance. Let me check if it's moving. Yeah, this basically forces. So another problem we said, the moored ship. You can see that one ship is moored and other one passing by. Yeah, so the mooring, usually you have mooring lines. You have this stern line, this is a bow line, and you have these two as the breast lines, these two, and these two are called the spring lines. So this is the mooring normal arrangement. So here the thing is, when the ship moves in this direction, it's difficult to move the ship, pull the ship, even though the attraction force is high, because the resistance is high in that direction, isn't it? If you want to move it, the resistance is high, added mass is high. So all these things make it difficult to move. So the impact of the interaction force or the excitation force which created by the interaction is going to be less. Whereas when the ship moves, this ship moves, you can see that if it's going to oscillate in this direction, the resistance is minimum, added mass is minimum, so the dynamics is more. So when the ship dynamics is more, that is the motion is more, that will translate that dynamics to the mooring system, and most of the failures of the mooring systems in such cases are reported happening from these lines. That is a stern line and bow lines. Okay, these are the forces acting on the moored ship due to the passing ship, as I said, picked up from the report. It's not, yeah, it's slow. Yeah, this is a diagram which shows that what would be the effect due to the separation distance of the two ships, and also size of the ship. You can see LP, this is passing ship to mooring ship with that size, and the separation distance. And you can see that how it's going up. This is the moment, and this is the sway force. So this basically indicates that when the separation is less, and if the size of the passing ship is very high, then you will have a severe effect. These are equations which deals with the mooring line force estimation. The typical case has been studied with this in this that is giving the moored ship particulars, and then row particulars is given here, including the braking strength and all that, and all these parameters given. So this shows that the forces, this is a force, the lateral mooring, that is, as I said, the breast lines, and this is in the lengthwise, the mooring lines, how it's going to respond. You can see that here the mooring forces, subsides fast because the transverse motions or dynamics are not significant, whereas here you can see that the mooring forces can go beyond the excitation force, interaction forces, because of the body dynamics, the ship dynamics. Yeah, and another case is what we discussed between ships. Here, when the ship operates in canals or waterways where the boundaries are close by, this you can say that. See, there is a constriction. There is a constriction here generated by the ship when it's adjacent to the boundary, which results in increasing the flow velocity and drops the pressure. When the pressure drops, it gets attracted towards the boundary, to the canal boundary, and the ship will go and hit against the boundary possibility. So that is the collision occurring with the canal boundary. And when the ship takes a turn, you can see that the flow variations. Here the pressure is high because the distance is more and the velocity is less. So here you can see that the stern of the ship is close to the boundary where the flow is having high velocity, pressure drops, and then there's a chance of it getting attracted and hitting the boundary. So the forward side escaped, but the aft can go and hit. Similar pictures for the curved canals and all that when ship operates, all taken from internet. This is a relative size when a big ship passes by, how it's going to affect the small ships now. Yeah, another thing is what is the ship squat. What we have seen is hydrodynamics, the interaction between ships and boundaries. Another thing is what is the attitude of the ship when it enters the shallow water. When the ship moves, you can say that there's a flow underneath and the bottom is very close, and which can lead to, because you know that the boundary layer formation, if you know, it's the boundary layer is formed at the bottom of the ship and also the canal boundary, that's the canal bottom. And boundary layer thickness is, I think you know what is the boundary layer and what's the flow velocity inside the boundary layer. So here the boundary layer thickness is 0 at the forward side, and boundary layer thickness increases towards the aft. When the boundary layer thickness increases towards the aft, the restriction to the flow is more towards the aft. So that means the flow velocity increases towards the aft. When the flow velocity increases towards the aft, the pressure drops more towards the aft. So the ship has to sink more to compensate the lost buoyancy due to the reduced pressure. So that's why the ship trims. And in addition, overall, there is a loss of pressure, the ship sinks. Vertical, it goes down, and also there is a trim. The combined effect, you call it squat. So this is sorry, this is the effect. You as soon as you can see that from deep to shallow water, how it's going to matter at the flow variations at the ship forward side and aft side. Yeah, when the ship trims, when it's squats, sink and trim, naturally, one of the thing is the following changes are expected. It will happen. One is the wave making. The wave making will be more, and if you look area far from the vessel, you can see that the energy of the wave, as I said, it builds up in shallow water, and energy of the wave is proportional to the square of the wave amplitude. So when the wave build up, naturally the energy associated with the wave is more, and so that means ship is losing so much energy. Law of conservation of energy. So naturally the wave making resistance increases. One thing. Second thing is when the ship is in a restricted waterway, the flow velocity around the ship increases. When the flow velocity increases, the skin friction increases and frictional resistance increases. Another aspect is because of viscosity, boundary layer is formed, boundary layer separates, eddies are formed, which carry away energy from the ship system. So that is in many counts, the ship resistance is going to increase in shallow water. So from wave making, frictional resistance, eddy resistance, many components is going to go up. So naturally, when it increases, the speed comes down. This is a result of the squat, one of the result where it says how the speed and water depth influencing. When the speed is high and the water depth is reduced, you can see that it goes to a dangerous zone. These things, I think we have already discussed waterway restrictions and how the different, parameters which are going to influence. When the squat goes beyond a limit, there's a chance of grounding. The ship may touch the bottom, damage the propeller, and all these things happen, and stability become worse. The grounding, you must have studied stability in grounding conditions, all things getting worse. So the vessels are advised to keep a monitor of the underwater keel clearance whenever it operates in restricted waterways. I have already discussed the ship-generated waves. Ship-generated waves are, there are two types who have studied the ship-generated waves. One is called the divergent wave and the other one is the transverse waves. The transverse waves dies out fast, but the divergent waves, continue to propagate outward, and this will build up at a distance. And as I mentioned, the energy goes up, the wave-making resistance goes up. And usually, that is called a critical situation. When the vessel operates in shallow water, you generally don't use the conventional Froude number, V by root GL, for the ship, which is related to output. There's a parameter which determines one of the parameters determining the wave-making resistance in deep water. Instead of Froude number, here we use what is called, instead of L, we use H, water depth, which is called the depth Froude number. And if the depth Froude number is equal to 1, which is called the critical, usually 0.9 to 1.1, that's a critical range. So if the ship operates in that critical range, the wave buildup is very high. So if it crosses the critical range, it comes down. And if it's below the critical, which you call subcritical region, so it's okay. So that means H is a parameter there and speed is also a parameter which determines the wave making effect on that. So try to avoid operating ships in the depth Froude number range of 0.9 to 1.1. Another area which I also mentioned, that when the ship is going to have a squat, it's a trim by aft and sinkage, the aft area of the ship is immersed more, the hydrodynamic forces are coming more in the aft region, which make the ship to be more rigid in the direction. It is difficult to change the direction of the ship, so which obviously indicates that turning the ship becomes difficult. So when the ship enters the shallow water region, the ship become less responsive to the radar because course changing become difficult because it's become predominantly directionally stable. So that is another thing why the ships don't operate on its own. Big ships, when it comes to the port, it don't operate on its own. You use tugs to push and pull and all that to take it to the port. So it's difficult for the ship to. Other option is if it's having the propulsive systems which can take care like azimuth propellers and all that, or both thrusters and all that, then it can go on its own. But with conventional propeller and rudder, it's difficult. So here the circle shows that from you can see the inner circle shows for the deep water condition and what happens to the turning diameter of the ship when the water depth keep decreasing. So we can see that the outer one is, I think, 1.2 H by T. That is the draft water depth to draft ratio. So which is a severe one. It takes which needs a longer space for a full turn. Yeah, these are things I have already discussed. One more thing, what you have to do is, as I mentioned before, in shallow water, the radar effectiveness reduces drastically, and propulsion effect also reduces drastically due to the flow radiations. This is a zigzag maneuver. I'm not going to the details of the parameters and all this. Okay, this is another ship. This is a benchmark ship model, which is called the KCS container ship, which has been extensively taken as a benchmark ship for the research studies related to maneuvering and other related aspects. So this model has been made and this has been tested at IIT Madras in the IIT Madras towing tank. And what you see here is a test done at the seakeeping maneuvering basing at NSTL Visakhapatnam, the naval lab at Visakhapatnam. So you can see that the turning maneuver, but this is a deep water condition. You can see this is it is fitted with its own propeller, rudder, and everything. It's propelled on its own. It's a free running test, and it's taking a turning maneuver to just study what is the turning of the vessel. The model in the deep condition. So this model was made at IIT Madras, taken to NSTL, and the students they did with the help of NSTL scientists. Yeah, so maneuvering, people who have studied ship maneuvering, you know that there are different equations of motion for the maneuvering, and you need to estimate the hydrodynamic coefficients appearing in the equations of motion to simulate the ship trajectory, which are extensively used in controls and everything. And so you need to find out the hydrodynamic coefficients. One of the widely used technique is called PMM, which is a planar motion mechanism. So now the same thing is simulated in this is CFD analysis. What you see here is this is a CFD. There are different modes for the PMM. This is a pure yaw mode with the CFD environment. So from which you get the forces, force history, and using the force history, you can determine the hydrodynamic coefficients which appear in the equations of motion. Yeah, this is the same thing for the turning side. It's a free running model. It's a propeller is model, rudder is this model, and now it is given a free running in the CFD environment to find out the turning. And these values are compared with experiments. Now, what is the interest in restricted water? So it's coming up. Yeah, this is a zigzag again in CFD thing, which has been done as part of one of my students' PhD work. So this is a facility which has been developed at IIT Madras with the funding from Naval Research Board. So this is the first of its kind in India. So far, it's remains so. That's a PMM mechanism developed indigenously, designed and developed and installed and operated. So it's validated with the NSTL facility. And so you can see that the models, this is basically a towing tank, which is to which add-on facility is put, is a PMF facility. And the models are run in different modes, and from which you get the force history in different modes. As I said, maybe pure yaw mode, pure sway mode, or combined mode, and all that. So the force history, from the force you can analyze and get the hydrodynamic coefficients. Yeah, so there's an interest in studying shallow water. Most of the towing tanks are, deep water facility. Now, IIT Madras, as part of the project, we developed a platform which can be, the depth of which can be adjusted, so that maybe you can do for different H/T values and all that. So over which you do that PMM analysis. You can see here, the platform is developed. You can adjust the platform, and the same PMM is used here. So that means you get the required information when the ship operates in restricted waterways, in shallow water or different water depth. So this information will go into the equations of motion, and you then can simulate the trajectory of the vessel when it operates in shallow water. These are the force histories obtained from the test. That's all. So just if you look to summarize, I've just said the hydrodynamic performance of the vessel in restricted waterway operations. So we have touched upon the hydrodynamic interactions, ship proximity and other parameters, chance of collision, then the forces acting on small ships, how it's going to matter when during interaction. There's a chance of bank erosion because the waves generate or flow generated by the ship, which can lead to bank erosion. How its effect on mode ship, then effect on wave making. We have discussed viscous resistance, maneuvering qualities, sinkage, trim, squattering. So these are the various things which we covered in this talk. So if you have any questions, I don't know. Likely half an hour, so I've taken not much time. So if you have any questions, which can.
Sir, especially in Cochin Port, the two rivers come and meet at Cochin Port. So there will be a cross flow of current. So what will be the combined effect of passing by ships when the current is there?
That's an important question. See, particularly if the current and the ship movement are going to be in the same direction. So naturally, we will consider it's a combined effect is added together. Current velocity and the ship velocity, isn't it? So if it's the opposite direction, we take the difference of that. So when you consider the ship flow, the speed of the ship, you have to include the ship speed plus the current speed as a resultant speed for that case. So that should be considered, because suppose the ship is moving at 5 knot speed and the current is 2 knot. So you have to consider that if both are in the same direction, you have to consider that it is moving at 7 knot speed. So when the speed increases, then the direct effect will be more. So the analysis should consider that, the flow, the current effect.
Cochin Port, there is a cross flow towards
Cross.
That means ships are moving like this.
Is it the opposite direction? Sorry, okay. No, then you have to consider what is the effect of the drift introduced by the current to the motion. So one thing is you have to consider the interactive effect. You can bifurcate the problem. One, due to the still water and its interaction effect due to the movement of the ship. Then there's another effect coming due to the current. So both should be added. And naturally, if it's a cross current, it can be against or in the same direction of the, of the thought shift direction. So you have to decide whether to increase or decrease that add or subtract that. Okay. That's all done. Okay. Thank you.
Thank you, sir, for delivering the first keynote. As a token of gratitude, we are handing over the keynote certificate for Krishnagudi, sir. I invite the head of department, Madhiragan, sir, to give away the token of gratitude or certificate and a memento. Now it's time for the announcement of the chair and the co-chair. The chair for the first session of this iCANOE is Dr. Krishnagudi, sir, and the co-chair will be Dr. Manoj T. Isaac, sir. So I'm handing over the session to the chair and the co-chair, the first session of iCANOE. Thank you.
Yeah, we'll start the first session. Only two purposes scheduled in this session. And let's see whether the presenters are here. Nandana Gopan, see you there. And Sharat Raj, who is the second presenter. They are there. Okay, maybe you can come to the front and take the seat. Yeah. Nandana Gopan, you can start with the presentation. I think so. You have only 15 minutes. Maybe restrict the presentation to 10 minutes. 5 minutes for discussion. Okay. Thank you.
Good afternoon, everyone. Myself, Nandana Gaban from NIT Calicut. Today, I'm going to present my research on CFD analysis of hydrodynamic performance of biomimetic marine cycloidal propeller under the guidance of Dr. Anil Kumar Das, NIT Calicut. These are the contents which we are going to discuss today. And coming on to the introduction, marine cycloidal propellers are propeller which are rotating about vertical axis. This marine cycloidal propeller having greater demand in terms of maneuverability. In case of a conventional screw propeller, they are having limited agility, whereas a marine cycloidal propeller provide 360-degree thrust. So they are ideal for tugboats, AUVs, and dynamic positioning ships. Even though improving their hydrodynamic efficiency still remains as a challenge. Here comes the idea of incorporating biomimetics into a marine cycloidal propeller. And coming on to the literature review, the study of Henry and Milton Martin in 1959 and iCANOE in 1961 is the key milestone in the study of a marine cycloidal propeller. And later on, several studies happened on this area, and Desai et al. On 2022 put forward a CFD-based hydrodynamic modeling in this. And my present research focus on bio-inspirations in this marine cycloidal propeller area. And coming on to the objectives which I put forward, to develop a one-way CFD fluid structure interaction framework for a three-dimensional marine cycloidal propeller, incorporating biomimetic inspired blade modification for enhanced hydrodynamic efficiency, and to evaluate the hydrodynamic performance and structural response of a conventional marine cycloidal propeller under varying flow conditions. And this is the methodology which I have gone through. Literature review and bio-inspiration, and then I have validated my simulation setup against a four-bladed MCP and the 3D modeling of both conventional and biomimetic MCP and the comparison of their results. And this is the validation part which I have gone through. Bhaktiyari and Gesemi 2019 2.5D numerical study on open water hydrodynamic performance of a oceanated propeller. Here, I am considering 6 zone, which is having four aerofoil blades on, and here I am considering three key parameters. They are thrust line indicates my present study, and the blue and yellow ones are the results which I have validated with. It's showing that there is only 5% error with the result. That my CFD results are almost, CFD setup is almost accurate. And this is the graph of advanced coefficient versus efficiency. And let's move on to the CFD analysis of a conventional MCP. I have modeled a 3D MCP in ANSYS Fluent. A conventional NACA section is selected, and the dimensions are given based on the journal Prabhu et al. 2022. And this is the mesh generation. For a fluid domain, I have given a mesh size of 50 mm, and the central propeller disc is having a size of 10 mm to accurately capture the effects. And this is the solver setup. The inlet is given as a constant velocity inlet, and the outlet is a pressure outlet. And we couldn't directly give the velocity in ANSYS Fluent. So I have using the equation of the advanced coefficient lambda equal to inlet velocity by omega. I have calculated the inlet velocity and given it as the input. And the thrust coefficient, torque coefficient, and efficiency are calculated using these three equations. And here comes the biomimetic part. I have taken reference from the recent journal ICRAM et al. 2025, and I have, this is a simple aerofoil. I have given two leading edge fins like a shark's dorsal fin. I have selected a standard NACA section for this. And this is the modeling of a biomimetic MCP. The fluid domain, inside the fluid domain, the propeller disc is there. In the leading edge, I have given two fin-like protrusions. And this is the meshing and simulation setup for the biomimetic MCP. And this is the graph showing advanced coefficient versus thrust coefficient and efficiency. Throughout the result, we can see an increase in advanced coefficient compared for a biomimetic MCP compared to a conventional MCP. And the efficiency is also increasing for lower advanced coefficient. And this is the graph which is plotted for advanced coefficient versus percentage increase in efficiency. For the lower advanced coefficient, we can see a higher improvement in the efficiency. And these are the key findings which I have gone through the work, that efficiency began to increase in lower advanced coefficient. But as it moves on, as the advanced coefficient moves on, the effect also decreases, and the thrust coefficient always shows a small positive gain, and the torque coefficient is slightly lower for all values, and the overall trend shows that biomimetic advantage is strongest at low advanced coefficient. And these are my references.
Yeah, now it's open for discussion. If you have any questions, you ask.
Good presentation. What was your 3 questions? What is the Reynolds number? Okay. What was how many million cells did you use? And how many million cells did you use? And what were your values of Y-wall plus?
2.7 million cells were used, and the Reynolds number is 1400, and the Y plus is calculated based on that coherent number calculation I have done, and that is given based on that.
Anyone else?
So now I've seen that you have shown the Voigt Schneider propeller, which usually has 6 leaves, right? And for you, there the thing is, it's basically a rotation about the vertical axis, and vessel is moving, it's having a forward speed, and the resultant velocity is taken to the blade, and from which you find out the forces, hydrodynamic forces, and which comes along the longitudinal axis of the ship, it does a thrust, right? So here, what is the mechanism here for that? Why it's called biomimetic? Yeah, it's going back again.
Sir, I have given some modifications like that is inspired from a shark dorsal fin.
Oh, it's only a dorsal fin. Okay.
Yes.
But
This modification I have the leading edge of the aerofoil.
you are trying to replicate the shark fin.
Yes, sir. Shark
That's so.
dorsal fin I am plan to replicate.
And how is the shark fin generating a thrust?
Sir, for marine animals like sharks and dolphins, there is a mechanism like their vortices shed like.
But that comes off from oscillation.
Yeah.
But here is it, are you oscillating it here in this?
The propeller is rotating and the blade itself is rotating about its axis.
Rotation and oscillation are different. I'm just looking to the basics of it. So oscillates means it goes like this, it's a mean position, and rotation means it goes all the way. And okay, so have you looked into you said oscillation? Important thing is, have you checked the straw hole number or anything? Oscillation, vortex shedding, straw hole number. Have you heard of it? Maybe look into that. Because people will ask whenever you talk vortices and all that, always related to straw hole number. So you keep that in mind. And when you are saying that the 6 fins are used, and how do you find any interactive effect between the fins, the flow between fins? Interaction. Look into that, because when you consider 1 fin and now you have multiple fins, 6 fins. So what is going to be the hydrodynamic? Whether it's going to have a constructive effect or destructive effect? Maybe whether it's going to improve the condition or reduce the condition. So you look into that part. And when you say it's a NACA section, aerofoil section with the diagram, what you've shown here now, it is not an aerofoil section, what you've shown. You know what is an airford section? Huh?
Sir,
You
this
should,
is a journal photograph only.
no, whoever gave it means don't copy the wrong thing, but draw the right. What is which NACA section you have used now?
NACA 0012.
12 NACA. Okay. Okay, that's all from my side.
Six, sir.
Just one question. In one of your slides, I've seen like 2.5D numerical modeling. So can you explain what you mean by 2.5?
Sir, 2.5D numerical simulation means the depth is not fully considered. For decreasing the simulation time in ANSYS Fluent and all, we are choosing this kind of modification. That is done in that journal itself. The depth is not fully modeled. Only a part of depth is given for the fluid domain. That's not fully 3D, not 2D also, but it have the effect of 3D.
So does that mean that your fluid domain doesn't extend the entire depth of your blades?
It goes beyond the depth of the blade. Actually, in a 3D simulation, I have given a depth of 18 meters. In that thing, I have given in the 2.5D simulation, there is a depth of 3 meters only for the fluid domain. So it couldn't completely get the effect of 3D simulation, but it will help to reduce the simulation time. And will give almost similar result to a 3D simulation also.
One last question. You said advanced coefficient. Usually for propellers, you say advanced coefficient is equal to VA by NT. How you define the advanced coefficient here?
That both are same only, sir.
Same, the diameter of the disk you have taken as the D.
VA by omega.
VA by omega R. Okay. Omega is the
Rotate.
angular frequency, and you've taken the radius
Yes, sir.
of that. Okay. That's what.
While calculating, both will be same only. That equation also.
Okay. Okay then. If no other questions, give a
Thank you, sir.
Okay, we move on with the next presentation. Yeah, next, please.
Namaste. Good afternoon, all. I'm Sharath. Today I'm going to give a presentation on the topic numerical analysis of air water multi-phase flow for thermal destratification in ship and offshore storage tanks. So these are the outlines of today's presentation. And coming to the introduction and motivation. So what is meant by thermal stratification and what are the disadvantages of stratification in offshore tanks? So as we know that in offshore tanks, mostly it is filled with like a CNG or LOX, etc. So whenever it is contact with external heat source, the heat will infiltrate inside the tank, and the liquid near to the tank will heat up and it will become less denser. And what will happen? The less denser liquid will go towards the ullage area through the wall, and due to this movement of liquid, the temperature along the vertical axis or the central axis will no longer be uniform. And this particular temperature gradient is known as the thermal stratified layer. And what is the disadvantage of thermal stratification? As the time enhances, the thickness of thermal stratification increases, and the uppermost layer which experiences larger temperature, which will ultimately goes to saturation temperature, and also it will attain saturation pressure also. So obviously that will lead to the pressurization inside the tank. So in order to avoid this pressurization, and the pressurization inside the tank, the thermal destratification, that is the mixing of stratified layer is very much important. So in this work, we have done stratification by introducing gas bubbles. That is mainly it is a CFD analysis mainly done using open form software, that is open source software. So that is the introduction. And coming to the literature survey, these are the main literatures we have referred from literature from serial number 1 to 6. It is related to the works related to bubble dynamics. Why? Because why we have studied bubble dynamics? Why? Because the thermal destratification we are going to study, we will be planning to study using introducing gas bubbles. So obviously the bubble interaction with the bulk liquid is very much important. So we have done literatures in the case of bubble dynamics, and also a few two-dimensional analysis we have done. And based upon that two-dimensional analysis, we got some results, and that results we have incorporated in the analysis of destratification using air bubbles or introducing air bubbles. So coming to the next work, it is a work which was done by Jagadnathan et al., which is reported in Ultrasonics 2020-2014. So he has created an experimental setup like this. So the author has filled the water. 1/3 of the domain is filled with the hot water, and that hot water is temperature of 333 Kelvin, and cold water he has filled with the cold water 303 Kelvin. And this is a stratified condition, stratified temperature, stratified condition. So in order to destratify means we have to break down the stratified liquid layers. In order to destratify or mixing the temperature, he has that Jagadnathan et al. They have introduced transducers like cavities. They have inbuilt, or they have incorporated their cavities along the center line at equal distance. And horn, it is also a transducer which create this cavity and horns which will produce sound waves. And by using that sound waves, vibration effect will occur, and due to that vibration effect, the temperature, the stratified liquid layer become mixed up, and by that the destratification occurs. So on critical reading, I found that this particular work has three main flows. Obviously, it is an active process that requires external energy source. The second one is due to the prolonged usage of these two transducers, that is cavity as well as the horns, it will create vibration effect, create increase of temperature. So the ultimate aim of destratification is we have to reduce the temperature, right? But the prolonged usage of this particular transducers itself create temperature, increase in the temperature. The second one is the whole setup, it is costly. So based upon these three flow, we have formulated our objective. So these are the main objective. Here we have we have created our own solver with open form software. That is the base solver we have selected is Interform, and that Interform is isothermal solver, and we have created a new solver called Interthem temperature form, and that we have incorporated energy equation, and also by changing various mass flow rates, in inlet gas mass flow rates, we have studied the mixing of that happens inside the storage vessels, and also we have found out the bulk liquid temperature at various mass flow rates, and also by introducing one parameter we have introduced, that is destratification index. By using that destratification index, we have quantified the effectiveness of destratification. So that is the main objective. So coming to see, it is not working. Coming to the governing equation. So these are the main governing equation, the conservation of equation for mass, here we can see the V is the relative velocity that is calculated by summing up of the velocities of two phases or the liquid or gas phase, and the conservation of momentum, that is equation number 3. And in that PRGH is the pseudo hydrostatic pressure. In that equation, P is the static pressure and rho gy is the system pressure, where Y bar is the position vector. And that interform solver solves, or it values, or it calculates the density by summing up of the two phases of density of two phases. And here equation number 7, as I have mentioned, interform is isothermal solver. We have coded, we have given, or we have incorporated this equation in the already available solver in the form, and we have created our own solver to calculate the destratification effect. And this is the equation number 9. Equation number 9 is the transport equation for volume fraction. And here in equation number 4, VR is the relative velocity between the two phases. And obviously the interform, which works on the basis of volume of fluid method, VOF method, and that was developed by Hrida and Nichols. And VOF mainly uses these two equations, where alpha is the void fraction and the value ranges from 0 to 1. And for calculating the interface, that is interfacial surface tension force, the solver uses this equation number 13. And in equation number 13, phi is the curvature between two phases, and it is calculated with equation number 14, where n is the position vector. And for validation purpose, we have taken the works of Sahedi et al. We have taken that numerical as well as experimental works. And here you can see, this is the that is a void fraction contours published by Sahedi et al. And the corresponding void fraction contours that we got from the solar interform is we have plotted here. And for quantitative measurement, we have plotted the detachment time at different densities, and it is found that the validation results found that the result is less than 4%, showing the solar is good for the present analysis. And again, we have taken the experimental analysis done by the Sahedi et al. In that one, we have calculated, we have found out the equivalent bubble diameter during the verge of detachment of a bubble. And that value was, the relative error was 7.77%. So this is the main flow diagram or algorithm or diagram of, algorithm or steps of that interform, and the main modification we have done to create the new solver in that form. And here we have done the main modification. We have added the code for energy equation, and also we have modified the solver by incorporating that variable property as a function of temperature. So this is the, and also that intertemp form or the interform works based upon Pimble algorithm. That is a combination of Simple and a piezo algorithm. So this is the main algorithm which is currently working for our newly developed solver that is using OpenFOAM. And these are the main codes where we have modified. This is the already available code in the OpenFOAM, and the main modification we have done by incorporating the energy equation. Here, the energy equation we have incorporated in the code. And for setting up the case file, we have taken a case file, that is a case file of a dam break analysis. And the main code changes are, or the code changes are done here, and the alternation or code changes done here are given here. And this is the thermophysical properties as a function of temperature that is incorporated in the solver. That code is also given. And for validating our newly developed solver, we have taken the works of Neil Dean and Neil Coopers. That work was published in Chemical Engineering. And these are the void fraction contours. Here, these void fraction contours, they have plotted using ANSYS, and corresponding void fraction contour we have obtained from the open form. And the relative position and void fraction contours, it shows that it is matching with each other. And for quantitative validation, we have taken the variation of a dimensionless heat transfer coefficient at different positions. And also it shows that the relative error is less than 4 or 5, 5%. And one more case we have taken for validating our newly prepared solver, that is two bubble case. Here also we have taken that dimensionless heat transfer coefficient, and the relative percentages within the limit. And this is the main boundary condition used for the storage tank. Here it is the inlet, and the vessel, the wall, it is defined as a no slip condition, and the inlet velocity inlet is provided here. And the wall for thermal stratified, for creating thermal stratified layers, we have taken the equation by Sun et al. And by using this equation, we have created the temperature distribution like this. This is a thermally stratified liquid layer. And this is the mesh we have. For creating the mesh, we have used a star CCM plus, and it is for mesh independent studies. We have obtained like the analysis is done with the mesh number of 12 lakh. So results and interpretation. So this is the main combination of void fraction and temperature contour. It is seen that the bubble is moving up, and the stratified liquid layer, it goes on depleting due to the interaction with the bubbles. And here you can see the combination of or combined void fraction and temperature contours for inlet gas rate 0.2 meter per second and 0.8 meter per second. And this is the distribution of bulk liquid temperature. And here you can see that the bulk liquid temperature or the homogeneous temperature distribution will obtain for a higher distribution or higher mass flow rate, that is 0.8 meter per second. And the homogeneous temperature distribution will obtain at a time of 20.3. And for 0.4 meter per second velocity case, that time was around 32.5 seconds, and like that you will get the information from the graph. And this is the main. Okay, thank you. So sir, this is the conclusion. Just we have started our CFD analysis only. We have started with inlet gas velocity only. And these are the description of future work. We will be considering this one, that is a source stream, and we will be considering that evaporation that is occurring at the ullage area. And also we will be going to optimize based upon the result by using some sort of AI software. We will be going to optimize the design for with what inlet gas velocity or with what type of inlet distribution we will get the destratification or effectiveness or destratification within that time. So these are the main future works we will be going to study. As of now, we have started our work, and as of now, we have developed the new solar with the open form. And this one can be just we have studied or started that work using water system only. And after we are getting much more results, we will be considering the actual cases like CNG or LPG systems or LOX, HE systems, etc., etc.
Okay, thank you. It's open for discussion.
Many things were mentioned. Okay, what is the cause for the stratification, and whether the cause remains there during the time that the bubbles are going up?
Yes, sir. Yes, sir.
What's the cause?
Cause means cause of stratification.
Yeah.
Sir, obviously, see if offshore applications or a ship which is carrying CNG or liquefied oxygen or LNG, LPG, or any kind of liquid, that temperature obviously, it will come inside that tank, right? And that due to the leakage of that temperature from the outside temperature, even though the tank is insulated, there is a chance of the temperature leakage from the outside source, from sun radiation, etc., etc.
So if the cause is still present in your analysis, you have to include the effect of the cause.
Yes.
So whether that has been included? If you don't include it, by itself, because of diffusion, the temperature will become uniform throughout the tank.
Sir, as of now, we have not included the cause. We have just taken that values from already published data.
What is the size of the bubble as it is going up? The size of the bubble will change. And what is the size of your mesh with respect to size of the bubble?
Sir, there is a chance of artificial coalescence of a bubble that will happen. So we have taken, in order to avoid that coalescence, bubble coalescence, we have taken a size 0.2 millimeter. We cannot control the bubble size. Whenever you are giving inlet velocity of or mass flow rate, the bubble it will generate by following that VOF algorithm. So the bubble, that shape of the bubble and the size of the bubble, that is uncontrollable. That will goes on changing.
What is the size of the mesh?
Sir, I will show an animation. Excuse me. Excuse me. That animation, you just show me that animation. You can increase the speed. You just escape that PPT and take that. Yes, PPT, you just escape the PPT. Yes. You just, can you increase the, speed? A little more you just increase. Here like this it is happening that when the temperature, when the inlet velocity for the air is given, the bubble it will create, and it will go on uncontrollably in all direction, in Z direction, Y direction, everything it will goes in all direction it will go, and also it will create waves. I have studied different kinds of waves. In minute level we have gone. Based upon that wave, we have again classified waves like type 1, type 2, type 3 waves are there. That we have not, I have not included in this PPT. So this is the destratification, stratification and destratification.
Question is, what is the size of the mesh with respect to size of the bubble?
Bubble, sir, 0.2 millimeter we have taken like that, 0.2 millimeter.
Whether there is any boundary layer in this problem?
No, sir, we have not considered so far. Boundary layer.
How many million cells have you used?
12 lakh, sir. 12 lakh.
12 lakh. Okay. Okay. Thanks.
Previous 27 or something.
Oh.
I came in the end only, but still.
27.
Slide number 27.
Okay.
Can you explain why there is a difference for that green graph? So out of curiosity, I'm asking.
Sir, this one now. Sir, obviously that from the animation you have seen by mixing the temperature, the stratified temperature, obviously the homogeneous setup will happen, right? So as the time increases, the temperature reduces down, and here in this particular case, even though the time increases, the homogeneous temperature won't change, and because of that only, at particular this point, the temperature remains constant, and because of that only it is coming like a straight line. Are you getting my point, sir? You are mixing the stratified layer. You are introducing bubble, and even after you are introducing the bubble, it will give the same value, right? Homogeneous because all the stratified layer it is destratified. There is no point of giving extra more introducing bubbles. Like here, from hereafter, you will get a straight line only. Because 750, 760 like that. We are taking.
This is basically, I'm just trying to understand what you just presented, what you studied. Suppose you consider, liquefied natural gas
Yes.
carrier or maybe LPG and all that.
Yes.
So what you're saying is that there will be a different layers of based on the density and
Yes, sir. Yes, sir.
temperature.
Yes.
That's called as stratified.
Yes, sir. Yes.
And you assume that a particular layer is having a constant temperature,
Yes,
right?
sir.
Same temperature over the layer.
Yeah.
Okay. Now you are actually trying to put air
Through the inlet.
bubbles from the bottom.
Yes, sir. Yes, sir.
So that the stratification can be destroyed and you can make it uniform.
Yes,
right?
yes, sir.
So what is the importance in making it uniform in handling the LPG tankers and all that?
Sir, uniform means, as I have mentioned earlier. Here it is the case, sir. Here you can see as the stratification, what happens through this wall region, the stratified liquid layer accumulates at this ullage area. And what happens is that it will experience, the uppermost layer will experience higher saturation pressure. And ultimately, there will be an increment of pressure that will happen in this region. So there is a chance of structural instability, or there may be a chance of bursting the whole vessel itself. So in order to avoid that thing, we are destroying the stratified layer by introducing bubbles.
To avoid the concentration of pressure and
Yes,
building of
yes, sir,
pressure
yes,
from
sir, yes, sir, yes, sir.
Okay. No other question. Thank you for the presentation.
Okay, sir.
Please give a clap.
Okay, sir. Thank you.
Yeah, I think it's now the mic is to the coordinator.
So the session 1 will be continuing after our lunch. Deva, you can.
This marks the conclusion of the forenoon session. We will be resuming the afternoon session by 2 p.m. So now we are having a lunch break. The lunch is provided on the first floor. Everyone, please enjoy the meal and come back soon. Thank you. Now, let us move on to the second keynote session. The keynote speaker for this session is Dr. Ronnie Francis. Dr. Ronnie Francis holds a BTech degree with first rank in naval architecture from CUSAT. He obtained his MS and PhD both in ocean engineering from IIT Madras in 2015 and 2024 respectively. He joined the DRDO as a scientist at NSTL, Visakhapatnam in 2002. During his tenure at NSTL, he worked on the hydrodynamics of marine platforms and towed bodies, as well as the development of autonomous underwater vehicles. He joined NPOL in 2008 and currently works as Scientist G and Division Head, Ocean Engineering. His areas of interest include computational fluid dynamics, flow-induced noise, and the design and development of underwater towed bodies and mechanical systems for sonar applications. He's also the project director for the acquisition of an acoustic research ship for DRDO. I now invite Sir for the keynote speech.
Thank you for the introduction, and I thank the professors and students of this department for giving me an opportunity to come and present the keynote address. So I am Dr. Ronnie Francis, Scientist G, working at NPOL, which is just about 2 kilometers from here. You may be quite aware of NPOL, and we have very close interaction with the Department of Ship Technology for over several decades. Whenever we need scientific support, especially from the academic areas, we contact the department, and they have been supporting us through many various CARS projects and all, which we have executed over the years. So a close relationship is maintained with the department, and we are going ahead in several projects with the support from the department actually. So I'll move on to the keynote address, which is the underwater radiated noise from marine platforms. So the topic content will be like this. I'll briefly talk about the significance of URN. URN is underwater radiated noise, and the nature of measured URN from a ship, machinery induced noise, propeller noise, and some methods for mitigation of this. So these are the significance of underwater radiated noise. Basically, it has got significant effect on marine species. You know, the marine animals, they use sound for communication and also to gather information about the environment and locate mates, prey and offspring, and escape danger and navigation. All these purposes, these marine animals use the sound. And the noise, unfortunately, from shipping occurs at the very similar frequencies as those of these marine species. And because of that, they get confused, or it has got a very detrimental effect on their day-to-day life in the ocean. Second is the effect of operation of sound-sensitive equipment in the sea. You know, for various scientific purposes as well as for military purposes, we deploy scientific equipment into the sea, like oceanographic equipment or even military equipment. So they work based on the sound for their operation. So these are also will be their operation also will be critically affected because of the radiated noise present in the ocean environment. And the third is one of the most important aspect of this. Mainly, this is the stealth of military platforms. You know, basically the submarines and ships in the military platforms, they have to be stealthy. If they generate a lot of radiated noise, they will be easily detected. So this is an area actually a lot of research is going on in the underwater radiated noise with respect to the stealth of military platforms. And URN is a combination of tonal sounds which occur at a very narrow frequency range to about 100 kilohertz, you can broadly say. So the IMO released the guidelines in 2014 for the primary source of URN, which are the propellers, that's the primary source, then onboard machinery, and flow noise due to flow around the ship's hull. These are the major sources of noise coming from the underwater platforms. And these guidelines were revised in 2023, increasing awareness on URN and in improving energy efficiency. Both greenhouse gases and URN are reduced. So there is a synergy occurring there. So if you try to reduce the URN, that is having a major positive effect on the reduction in the greenhouse gases as well as the efficiency of various machineries on the platform. So this significant synergy offers opportunity to reduce the URN as a co-benefit of energy efficiency measures. Next. Are you operating or I am operating? Okay, fine. So we'll look at the nature of the URN from a ship. Basically, I have taken this based on measurements on a ship called MV Overseas Harriet from a paper in Arvesen, 1999. So this was a bulk cargo ship which had a low speed direct drive diesel propulsion. And the acoustic measurements were carried out at a distance of less than 600 meters between the ship and the hydrophone. A set of hydrophones was suspended underwater with the depths from 60 meters to 460 meters as a vertical line of hydrophones. About 5 hydrophones were used to record the radiated noise from the ship. And these hydrophones were calibrated to frequencies as low as 3 Hertz. And these are the wideband source levels from the measured radiated noise from the ship. You can see on the left side the speed varying from 8 to 16 knots. And you can see that the source level or the radiated noise level varying from 178 dB to 192 dB. So that's a broad wideband source level detected. Next. We will look at the radiated noise spectrum in a little more detail. You can see these are the measured spectrum from the same experiment I am telling at 2 shaft RPMs. One is at 68 RPM. That's what you are seeing at the bottom. And at 140 RPM, that is the top spectrum which you are seeing. On the x-axis, we have the frequency. On the y-axis, we have the URN level in dB. So if you see the keel aspect narrowband URN spectra at low speed, where you can see some notations like G. G stands for the ship's diesel generator. And B is the blade rate, propeller blade rate. And F is the diesel firing rate. So at low speed, you can see that is the 68 RPM spectrum at the bottom. The tonals from the 5-cylinder SSDG ship's service diesel generator. So basically, it has 5 cylinders and they contributed almost all of the URN. So at, you can see the bottom spectrum, all the spikes are having G. It is all coming from the diesel generator of the ship. And that diesel generator is having a narrow, the natural frequency of 6 Hertz. So all the complete spectrum, you are seeing almost entire spectrum is filled with the 6 Hertz and its higher harmonics. So you can see all the spikes as not good. You can see that G is at 6 Hertz, then the next spike is at 12 Hertz, then 16 Hertz is a half frequency harmonic, and 24 Hertz, etc. That is filled in that spectrum. Only 2 spikes you can see at 24 Hertz and 30 Hertz. This is the 24 Hertz and this is the 30 Hertz spike, which is contributing to the high speed spectrum. Whereas all other machinery induced noise is contained only in the low speed. So that's the idea. At the high speed, you can see that if you see here, this is high speed spectrum. At high speed, the propeller radiator related sources dominate the ship's URN. Next. So if you look at the high speed spectrum, you can see that this is a high resolution spectrum actually of the ship's radiated noise. The ship is powered by a two-stroke diesel engine, and its shaft is directly coupled to the propeller. So you can see this is at 140 RPM. 140 RPM. So the diesel firing rate is there are 6 cylinders for this engine. So the diesel firing rate will occur at 14 hertz. That is what is given in the, you can see here, the 14 hertz. And the blade rate, it had a 4-bladed propeller. So again at 140 RPM, the 4 blades will constitute 9.33 hertz as the blade rate frequency. So that's why in the spectrum, you can see every even harmonic of diesel firing rate, F is standing for the, you can see F is all the diesel firing rate of the diesel engine, and the B is the blade rate, propeller thing. And you can see only 2 Gs, but we have seen in the machinery spectrum, I had told that only 2 harmonics are coming in the higher speed. So that is what is seen here, only 2 Gs are there. Only at those frequencies alone, the contribution from the machinery is also coming in the high speed spectrum, whereas all other things are this Fs and Bs. So because of this combination of 140 RPM and the 6-cylinder diesel engine and the 4-bladed propeller, you can see every even harmonic of diesel firing rate F coincide with the 3rd harmonic of blade rate. So that's why you can see B6 and F4, similarly F2 and B3 and F6 and B9, they coincide, because that is how that sharing is happening actually. So, so this causes whoever is measuring the RPM will get ambiguity. This causes ambiguity in the sources of the overlapping harmonics. You don't know this noise is coming because of the propeller or is it because of the machinery firing rate at those frequencies. You can also see weak tones at intermediate firing, half firing rate, like 0.5 F at 7 hertz, from the F3, F by 2 and F by 2, like that also. Half harmonics are also visible in the spectrum. So this is a measured URN from the same bulk cargo ship. Basically, the ship's URN is given in dB, to 1 micropascal at 1 meter. The major mechanism of noise generation by diesel engine is because of the by the piston slap. The diesel engine cylinder is going up and down. So when there is a reversal at the top, when the reversal of the piston happens, it's called piston slap, which is the impact of the piston against the wall of the cylinder caused by the reversal in the direction of the piston side force. So that's what is causing the main source of generation of noise from the diesel engine. And you can see the FR, the firing rate, it is not increasing monotonically. At 10 knots, it is 175, but at 12 knots, it's only 170. Whereas 174, so there is no direct correlation. You cannot expect the URN level to increase monotonically with increase in speed. So in the table, you can see the fundamental firing rate, noise level do not increase monotonically with the ship speed. And likely that the dynamics of piston slap motions change with ship speed, which may cause significant changes in the spectrum of harmonics of diesel firing rate. Next. So this I'll skip. Next slide. So this is that's how the nature of the URN spectrum. If you look at in close, this is one of the very rare measurements reported in literature. You don't find this kind of literature very frequently in the open literature. So we have seen that. Now we look at what are the major sources of underwater radiated noise. Mainly the propeller, the electric motors, the diesel generators, auxiliary machinery and equipment, and water flow. These are the major sources of URN from the ship. Next slide. And there are, if you look at the machinery-induced noise, and the machinery-induced noise, as we have seen in the spectrum, dominates the URN spectrum below cavitation inception speed. Till the moment propeller is not cavitating, the machinery-induced noise dominates in the noise spectrum. But the moment propeller starts cavitating, the spectrum shifts to the propeller noise dominates in the spectrum. So machinery-induced noise is narrow band in nature. They usually occur at the firing rate of the diesel engine or the rotating rate of the shaft. So we have tonals at a particular frequencies, particularly below 200 hertz, and they get transmitted into the water through these three mechanisms. The airborne path, you can see there is an engine fitted on the platform ship, and there is an airborne path which is exciting the structure and then getting radiated into the sea. The second is a first structure-borne path where through the foundation, the noise vibration gets transmitted, and then it is coming to the hull and getting transmitted to the sea. And the second structure-borne path is like airborne path exciting this, and again that is getting secondary excitement from the hull. So this is how the machinery-induced noise is generated in the platform. Second, if you look at the cavitation-induced noise, as I told, the above cavitation speed, the propulsor-induced noise dominates, and this noise is broadband in nature. If you look at the machinery-induced noise, it is a mostly tonal noises where particular frequencies it happens. But at cavitation noise is broadband in nature, mainly because these cavities are there which occur at various sizes, from very small size cavities to very large size of cavities. And so their explosion generates sound, implosion generates sound, and this sound occur at a very wide range of frequencies owing to their varying size. So that's why it's broadband in nature. And also it includes high levels of tonals. Also their tonals are present. Tonal means the narrowband single frequency sound, which occurs because of the propeller shaft rotating. So you have the, if a single propeller is cavitating, then each rotation of the propeller, one cavitation cycle it will undergo. So that say that tonal or single frequency noise is also appearing in the spectrum. Next. So we will look at the machinery-induced noise a little in closer detail. Next. So these are some of the common mechanisms or methods to minimize the vibration coming from the ship. Mainly the vibration, if you minimize, noise will also subsequently getting reduced. So some of the popular vibration isolation mounts are these conical elastomeric mounts, the sandwich mounts, spring isolator mounts, wire rope isolators. These are all very commonly used onboard ships to reduce the noise and vibration from the ships. So these are all basically passive mounts. They are simply fitted. There are some elastomeric content inside that. So that elastomeric content will try to reduce the vibration, especially at high frequencies. But most popular, these are definitely fitted in almost all installations on board the ship. Next. So we'll look at the mechanism of this vibration isolation. If you look at this is a machinery, typically a diesel engine or some machinery fitted in the ship. And this is the vibration isolator, typically a mount which we have seen in the previous slide. And this is the ship structure. So there's a force when the machinery is running, engine is running, it is generating a force F1. And through the isolator, finally a source Fs is transmitted to the ship's structure. So the force of amplitude F1 at given frequency acts on mass m, and the purpose of the isolator is to keep the amplitude Fs of the force that acts on the ship structure within acceptable limits. So that is the purpose of the vibration isolator which we are trying to fit. So the ratio Fs by F1 is the amplitude is called the force transmissibility. How much force is generated by the machinery and how much force is finally getting transmitted to the structure. So that ratio is called the force transmissibility. Motion transmissibility is also given by exactly the same equation that can be proved. So if there is a displacement of some amplitude taking place at the machinery and the displacement which is transmitted to the ship structure, this also occur by exactly by the same equation given here. So the motion transmissibility are obtained by same expression where R is the excitation frequency ratio to natural frequency, and the damping coefficient, and that can be easily calculated for the particular case. So this is the motion transmissibility. So when we select a vibration isolator, we have to look at the motion transmissibility, how much efficient it is in transmitting or isolating the vibration. Next. So if you plot this, you will see a curve like this: motion transmissibility versus the frequency ratio. So on the here we have the motion transmissibility, and here the frequency ratio. If you look at this plot closely, we can see that for small frequency ratios, that is when R is very low, less than 1, this region where the transmissibility is almost equal to 1. So we can see that at small frequency ratios, the motion or force is transmitted without any attenuation or amplification. Whereas as you come close to this region of 1, where the exciting frequency come close to the natural frequency of the system responds at resonance. And a very large value of motion and forces are transmitted. And all curves will pass through 1 at root 2 as per that equation. When it is 1.4, all curves will pass through that. And right hand side of that point is the isolation range. So when this is the isolation range from here to onward. So when you select a vibration isolator, you have to select something which falls in that range. So that's what that last sentence. That's for good isolation. That is more transmissibility. One needs to choose an isolator with the smallest possible K. You have to choose an isolator with stiffness very less, smallest possible K. But problem is, you can say that I will choose a very flexible isolator, but then it will have its own large static deflection, which cannot be permitted in a ship. For example, if you isolate an engine with a very soft isolator, it will start to oscillate in a very large displacement, which is not permissible because first of all, it will foul with the adjacent structures, and secondly, it will also, you will have a lot of shafts and all running. So it will not be possible to permit such large levels of static deflection. So that's why those mounts which we have seen in the first slide are not that effective at low frequencies. They are good for, they are very popular and effective, but they are good for high frequencies. You cannot isolate very effectively for low frequencies, and there is a problem. Low frequency is the most problem in most of the stealth cases and all. You need to isolate low frequency because low frequency noise is what transmits to longer distances. So they are not very effective for the low frequency. So there are some mechanisms for this. For example, one very popular vibration isolator is the tuned mass damper, TMD. You can see in figure, this is a machinery fitted on the ship's structure, and that machinery is also vibrating. And that vibration typically comes like this. There is a resonant frequency, and then dies down. So that resonant frequency is a problem which we are trying to address. So what we can do is we can attach a tuned mass damper, which is an additional mass mounted with the flexible elements on the vibrating machine. So this is a tuned mass damper, this particular thing on the equipment, again with its own springs, so that they can be tuned to specific excitation frequency. And when the damper is correctly tuned, it can reduce vibrations dramatically within the area of resonant frequencies. So that's why you can see once you fit this, it comes down here at the resonant frequency, correctly tuned for this resonant frequency. That's why here the vibration transmissibility is very less, but it increases slightly there on outside that, but it's still acceptable because overall levels come down very much by this. So that's why by adding the damper, the vibrations of the main structure outside the intended damping area increases. That's why you are seeing here and here, it increases. And this was, Wärtsilä has developed and attached TMD to a turbocharger, and many units are in service. This is influenced reported by Wärtsilä for this tuned mass damper. Next. So this is a Wärtsilä system. Basically, you can see this is a turbocharger, and this is the tuned mass damper fitted on that. And this is the effect without damper and with damper. The RMS velocity of vibration comes down drastically. This is the Wärtsilä 9L46 engine on which this damper is fitted, and it has been in service in many units. So, and the mass required for a tuned mass damper, the mass required to achieve is about 5% of the total mass of the model mass of the vibration mode in question. So it is quite an engineering solution. It's possible to fit it on practical installations. Next. So again, you can obviously see the drawback of that. The tuned mass damper is tuned for a particular frequency. Whereas when the engine operates over a various speed regime, the frequency changes. So then it is not applicable over a wide range of frequencies. What then we do? We have to go for active vibration isolation systems, where this is a, you can see this, these are the actuators, three actuators, you can see this one, this is the second, and this is the third. These actuators will generate counterforce. So if you look at the rubber isolators are very effective, the point which I told earlier, but they should be sufficiently soft to attenuate low frequency vibrations. To improve vibration isolation performance, especially at low frequencies, active vibration is proposed. And they generate control forces to counteract the primary vibration transmission. So that is what we are seeing here. The vibrations of the generator housed in a tugboat, controlled using three retrofitted inertial actuators. And there is an optical tachometer marked B here, which record or which senses the vibration taking place in the machinery. And sensing that, a control signal, there is a control system is there, control mechanism is there, which generates a counterforce and makes these actuators, inertial actuators, to work at that particular frequency to counteract that. Next. So this is the effect of the active vibration isolation, which we have seen in the previous slide. The active vibration control system performed well for the first 1.5 and second engine orders with attenuation as high as 30 dB. 30 dB is a huge value of in terms of since it comes in decibels. Reduction in vibration is possible. And actuators, basically, that was an experiment because we don't have any data from the ship. It is very, very difficult to get the actual data from a working ship, and these values are not reported. Whatever which I have mentioned is from a experiment carried out by the Wärtsilä people, and the other one is again experimental papers which generated. Mainly these systems, these are costly systems, and these are difficult to maintain. So especially this active vibration isolation system, though it is very effective, it is costly, and you don't find in much of the commercial application, but you will find it in naval platforms. Naval platforms and submarines, you will find this because their cost, more than cost, the stealth aspect is very paramount. So these systems are fitted on many of the submarines and naval ships. And obviously data is almost not available because these are naval platforms and these data are classified. So we don't have. So this experimental data which we have received is this. You can see the major reduction in the vibration levels because of the active vibration isolation. And one of the outcome of their experiment is the actuators, which are very reasonably small enough so that, and these actuators can produce the force necessary for a real submarine installation, and they are sufficiently small to be installed in the existing engine mount installations on board the submarine. That is a thing, because these are small enough and effective enough to be installed on a, or even it can be retrofitted on a serving ship or submarine. So that is how. And active hybrid isolation mounts are currently installed on submarines, naval surface combatants, and oceanographic research ships. Next. So that I briefly covered the machinery-induced noise. I'll also talk about briefly about the propeller noise. Basically, the propeller noise are generated through a number of noise-generating mechanisms because of the tip vortex cavitation, which is one of the most significant source of propeller noise, and different types of blade cavitation, hub vortex cavitation, and pressure pulses due to wake inhomogeneities at the propeller plane, and also the singing of propeller. Singing is a very distinct narrowband noise due to the resonance between the blade's natural frequency and the trailing vortices. So there is a resonant vibration takes place, and that is called the singing of the propeller, which is very distinct and can be easily detected by very far away systems listening to this noise. And at low propeller speeds, narrowband noise at blade range, blade passage frequency, and higher harmonics is present. And once the propeller starts cavitate, at the propeller load increases, then the narrowband changes to a broadband cavitation noise due to implosion of bubbles of various sizes. And the narrowband noise due to fluctuating cavitation at blade passage frequency are also present even in a cavitating propeller. Next slide. So these are some of the very common methods of mitigation of cavitation noise. We have the contracted and loaded tip propellers. I will not talk on this in length because I have given a talk on this some time back. It is available in YouTube. If anybody is interested, can check that. Methods of mitigation of cavitation noise. Basically, we have the contracted and loaded tip propellers, Capel propellers, and propeller hub modification, where it's a PBCF. It's called propeller Bose cap fin, which is very effective in reducing the hub vortex vibration. Ducted propellers, you can see that blue color picture. It's a ducted propeller, and the geometric optimization of propellers are very commonly employed by increasing the number of blades, increase blade area ratios. These are all effective mechanisms to methods to reduce the cavitation and skew and vortex generator and the coating the propeller surface. So these are very common methods of mitigation of cavitation noise. Next. Yeah, I think I'll stop here. If I am any questions, you can.
Sir, it's a very good presentation in the sense that you give a lot of applications of vibration induced noise, and you mentioned about the vibration isolator. So the one thing that you focused is that if the vibration natural frequency is very low, then the only option is that we have to increase the stiffness. That means we have to use a heavy mass, or the flexibility has to be increased. My question is that which one is more important, whether the propeller you are saying or the machine? Which one is the one which causes most vibration according to you?
It depends upon the speed regime. At high speeds, the propeller, that's what the measurements show. At high speed, the propeller noise dominates the spectrum. It is completely coming from the propeller noise. Whereas at low speeds, till the moment of propeller cavitation, the noise is mostly coming from the machinery. And this has got, for a commercial or civilian ships, the important comes from the comfort of the passengers inside the compartments. So especially the machinery vibrations and all getting transmitted to the interior of the compartments, leading to sometimes very uncomfortable levels of noise within the accommodation areas. So then you find that there are, when you do these kind of measurements, you will find that some particular frequencies are there, which is creating this noise. Then the question is from where this sound is coming, which that frequency corresponds to what? That is the area, because if you have to address it, you have to identify the source. If it's such a vast mechanism, if it's such a vast system, there are so many machineries and propeller equipment running on it, and it is very difficult to pinpoint which is causing the problem. So then that's why these measurements are carried out, and we have to identify, suppose a particular machinery is generating that noise, then we have to look into it in closer detail. Then you will have to address that.
Go to that slide which shows the actuator connected to the machine or cell, to the machine unit.
I think 2 slides before. This one.
Yeah. So here, this is actually an experiment that they are planning. What is the input and output?
This is not, it was not actually, not only an experiment. They are actually retrofitted this in a tugboat, and the vibration levels were measured, but it was implemented on a running system.
So what's the vibration isolation technique they used here?
This is a active vibration isolator. So what is happening is a system, the tachometer which is mentioned there will measure the actual vibration taking place. And he knows at what frequency this vibration is happening. Then we have to generate a counter force which is out of phase with that vibration. So that is why this actuators A, B, C through 3As are there. They will generate their inertial actuators actually. There is a mass. There is a mass sitting inside electrodynamic inertial actuators. So there is a current passing through that. So there is that electrodynamism will generate vibration of that mass. And that vibration will take place out of phase with the engine frequency. So that is how that vibration can. So it is an active, it is not. So if the frequency of vibration is changing, engine speed may vary. Engine may go to a next higher speed. So that time vibration frequency will be different. So then again, this system will measure that vibration level and vibration frequency and generate a different set of counterforce to address that. That's how it works.
Thank you, sir.
Sir. Sir, I would like to know what are the new measures in isolating low frequency? What is the current scenario?
Yeah, isolating low frequency is a area of very wide research. So far, people are claiming so many things, but presently there are nanomaterials, those kind of esoteric things are being proposed actually. We in open use, it is not many systems are commonly available. This active system can be used. Active systems are available. Whatever you are seeing here can be addressed for low frequencies. But passive systems, like what we have seen in that mounts, those mounts kind of things for low frequency are presently in the nascent stages of research. But these systems can be used for addressing the low frequency vibrations.
Thank you, sir.
Can be used for both high frequency and low frequency, or generally preferred.
Yes. This system this is a versatile system. It can be used for any sort of vibrations. But again, that system will have that electrodynamic shaker or inertial actuator which we are using. It will have its own limitation. So within that range, it can be designed to address the low frequency vibration as well as high frequency.
So basically, it's going to identify the excitation force and create a counteracting force using a hydraulic system, or how is it?
This is electrodynamic isolator. There is a magnet and a coil, which is, there are so many types of this actuators are there. Inertial actuators are there. This particular one was an electrodynamic actuator, where if you apply a current, this will generate a repulsive force and the magnet and coil, then it will set the mass into, there is an inertial mass inside that. That inertial mass will be excited to vibration and that will vibrate out of phase.
Yeah, it should be out of phase. Right? Yeah.
So that will be, actually we don't need this system to attack high frequency vibration, because that can be easily addressed by these mounts. Mounts are there which are very cheap and you can easily replace it, which are maintainable.
No, I am asking low frequency may be okay, but when it comes to high frequency, the response time is going to be very less, isn't it? When it's high frequency.
Yes, that's correct.
So,
yes.
but still it can accommodate.
But that's what I'm saying. These systems, there is no need to have this kind of elaborate systems to address a high frequency vibration. Because high frequency vibration can be readily attempted by this passive isolators, that mounts and all. Isolation mounts and these are very cheap systems, which can readily address this problem. You don't need this kind of systems for high frequency vibrations, because this is difficult to maintain. It is costly. It consumes space. So commercial ships, unless there is a particular need, some particular low frequency component is there in the ship, which makes your life miserable inside the ship, and there is no other way to address, then they may fit it. Otherwise, these are you mostly find in naval platforms.
And for TLD,
TMD, sir, that previous.
No, that is that's a tuned mass damper.
Tuned mass.
Sorry, not big damper, mass damper. So, but it's, as you said, it's going to have only one frequency for that system. And naturally, you're trying to fit it at the resonance frequency.
Yes, yes.
And put a phase difference of.
That's why it's called as a tuned mass. It is tuned to
yeah.
that particular frequency. You make the measurements on that engine, and you find that one frequency is the resonant frequency, and that frequency is creating all the problems. So you estimate your mass and all based on that particular frequency, and make it out of phase. So that.
Okay, thank you.
You in one of your slides you showed different components or sources of noise, right? Like you have machinery, you have propeller and thing. And then you mentioned about this tuned mass damping. Can you use or can you tune one of these machineries in such a way that it can nullify the effect from the other component in?
Yeah, theoretically possible. Theoretically, it should be possible, but tuned mass damper has to be fitted on the machinery which is vibrating. You have to fit that mass on the particular machinery which is vibrating. You cannot keep it somewhere away and expect that to affect the vibe, because they are mounted on separate mounts. They are mounted on separate foundations.
Okay, and then you were talking from the point of noise radiation, right? But from a detection point of view, is it possible to identify where this noise is coming from? Is it possible to identify the individual components from its frequency?
That's why this kind of measurements are being carried out. We have a spectrum of noise that is there, which by looking at it by time series, if you look at it, you don't get anything at all. So that's why we do this kind of spectrum we'll generate with respect to frequency, and then try to identify this is a typical naval exercise which people carry out. We know, yeah, this frequency is coming. So this frequency, by intelligence and all, we know some particular submarines are known to have this kind of secret frequencies. So this should be that platform. That kind of analysis is to be carried out based on this. This is what they do in the naval scenario.
When they are all operating together, there will be a different scenario, right?
Still, see, if you look at that's what I'm saying. If you look at the ship noise spectrum, we don't know from where this noise is coming. Even from the ship itself, we don't know whether this noise is coming from the ship itself, because some of the propeller noise and all, these bubbles collide, implode. Implosion of the bubble take place. Sometimes bubbles travel aft, and some 100 meters away from the ship also they will implode. So the noise will look like coming from a very different ship. By the time ship would have gone ahead also. So then you don't know from where this noise is coming itself. The source of the noise itself is doubtful. It's a very difficult scenario, very confusing scenario to identify. That's why a lot of research is going on. But most of this research take place in the classified area. So open literature is very, very less.
Thank you.
On a next level of problem, I have my own ship and my own sonar. And then I want to, my sonar is detecting the ship, and I want to now silence my ship. If you pose the problem like that, then the rankings may change. In one of your slides, you had rankings for noise. Before you showed the Arvisan, can you go back? And it says, yeah. And you also mentioned that rankings depend on the speed. So if we have one particular scenario, then the goal should be, I want to quieten my ship.
Yes.
So that my sonar cannot detect it. Only if I pose it that way, it's a solvable problem. No, before this. So if you pose it like that, then we have a solvable problem. Then we have a real problem that we can attack.
That's why one ship for which I am the project director, that ship is an acoustically silent ship, which we are making in India for the first time. That is an acoustic silent class ship where the radiated noise levels are to be kept at a very, very minimum level. So as sir suggested, how to silence our own ship is a major thing. So you have to use a multitude of all these things which I mentioned, like using a propeller like that. or the engine mounts or active vibration isolation, this bubble implosion, even flow noise around the hull, shape of the hull, all those things will become very critical. So as a cumulative effect of all these things will make the ship quiet. There are a class of vessels called silent class vessel, you may be knowing. In now many classification societies are coming up with silent class ships. One is the DNV has got silent class A, R. There are two more classes, A for acoustic, R for research. So they specify the radiated noise levels from the ship. Similarly, now after that, ABS has started its own class for silent class, and the IRS has got its own URN class, underwater radiated noise class. So their classification societies are now specifying the silent class classification for the ships. And in India, we have in Goa, there is a underwater ranges. I don't know, you may be aware. In Goa, it is there where ships, naval ships are typically brought there, and there are measurement hydrophones systems are there, and the ship will run past that, and this URN spectrum can be recorded there. Again, there is a problem because Goa ranges and all are very shallow kind of things. You cannot make these measurements in shallow water. If you try to measure the radiated noise from a ship in shallow water of 30 meter depth or 40 meter depth, we'll find multiple reflections of sound. The sound reflects from wherever it hits. Bottom it will reflect, and from the sea surface also it reflects. So again, the noise you are receiving is a multitude of complex noise from different sources. So again, that measurements also get heavily corrupted. So this is an area where a lot of confusing things are available.
Heavy noise. Yeah. So like that for ships, is there any?
Yes. There are many systems there. If you have the hydraulic, these are only broad major noise mechanism. Only as I said, there are so many other systems in the ship, like the fluids running through ducts. There are hydraulic.
My question is there any classification society which says that the noise level should be less than a particular value?
That's what I just told now, that classification society got this class of ships are there. For example, in DNV,
A silent
DNV,
ship,
as per, like if you say ice class ship, DNV says silent class ship. And silent class itself, we have got 3-4 types of like silent A, silent R, like that is the silent S, like that silent AR, like that many classes are there. So they specify once the ship is built, you have to take the ship to the this measurement place, where they will measure the measurement which I had shown for that ship. Similar measurements are made, and it is ensured that the radiated noise from the ship is within that dB level. Basically, the classification society gives a permissible curve for the radiated noise. So you have frequency versus dB level. So at the different dB levels, typically it will go to some maximum permittivities of the order of some 170 dB, like that, where you can see that ship which I had shown, the level was going up to 198 dB and all. For example, DNV class says at 11 knots, your ship should produce only some 180, 175 dB of noise. If that is met only, that ship will be classed as DNV silent class R by DNV. Not only 1 dB value, it is varying with the frequency, but generally I am telling if that noise spectrum is maintained, then only the ship will be past the classification society criteria. So during the construction of the ship also, the class will engage, and they will ensure that what's the propeller you are selecting. For example, diesel engine is ruled out. If you want a silent class ship, then this directly coupled diesel engine or even with gearbox is more noisy. So these will not work. You will have to go for, because shafting will generate a lot of noise. So we'll have to go for diesel electric propulsion minimum. So diesel electric propulsion, you will avoid the complete shafting, and you will keep the diesel engine at a very high elevated place or with a lot of vibration mounts and all, so that no vibration, or you can keep the engine wherever you want, so that it will only generate the power, and power is taken to the propulsion motor, and complete shafting is avoided. So if you will find most of the silent class vessels are diesel electric propelled. And propeller also, you have to go for some ducted propeller, which not an open propeller, which will get a lot of cavitation and noise.
Thank you, sir.
Yeah. Thank you very much for watching this.
Thank you, sir, for the keynote speech. As a part of token of gratitude, we are handing over, uh, as a part of token of gratitude, we are handing over the keynote certificate and memento. So we invite our department emeritus professor, Dr. D.D. Ebenezer, to hand over the keynote certificate. Thank you, sir. Now we are moving on to the rest of the proceedings. It's time for the announcement of the chair and the co-chair. Dr. Krishnanguti sir will be continuing as the chair, and Dr. Fawaz TK sir will be the co-chair of this session. I am handing over the session to the chair and the co-chair. Thank you.
Yeah, good afternoon. Back to the sessions. Next session is on ship hydrodynamics. We have 5 presentations. Let me check whether the presenters are Shruti Raj. That's it. Okay. Shija is here. Yeah. Remisa. No, sorry. Rasima. Rasima is. Right? Yeah. Adhina. And Arjun. Okay, they all there. Okay. When so we have to plan it. So if somebody is missing, then you have to adjust the time. So you have given, I think, total 15 minutes, right? The last digit is not seen. 15 minutes, and please confine to 10 minutes presentation and 5 minutes discussion. Thank you. Please go ahead.
Good afternoon, everyone. I'm Shruti Rajesh from Department of Technology. I'm a PhD scholar over here. So what I'm presenting today is about the wave and total resistance of the wiggly hull using computational methods. And these are my co-authors. Moving on to my discussion, the paper that I have presented. As the demand for having a hull with minimum resistance and with high velocity is being increasing over the years, the need for optimizing a hull also is being increased. And as over the years, the use of computers have been increasing, and therefore CFD, the computational fluid, prevailing use of computational fluid dynamics are also increasing. So in order to optimize, our aim is to minimize the total resistance of a hull. For that, what we are trying to bring in is that what it has been already used in this. First, the variants that have been created for minimizing of resistance are being analyzed in the potential flow solver. That is a software that is dedicated for potential flow. And then analyzing the best hulls that are chosen from this potential flow solver in a total viscous flow. That is to analyze for the total resistance. For that, I have taken a preliminary analysis with the wiggly hull, a simple equation hull that can be defined using a single equation as shown in the PowerPoint. And that has been used as a preliminary analysis only. So here what I have done is analyze this wiggly hull using in potential flow first, and then analyze the same wiggly hull in the total viscous flow solver to analyze in the total resistance. For that, a potential flow solver in ship flow has been used to analyze, and the total resistance is computed using OpenFlow. So these are the major things that have been done in this paper. So these are the dimensions of the hull that has been chosen in. As seen in the left side, you can see that there are many analyses that has been already been done with wiggly hull. Experimental results are already there. And there are various hulls that people around the globe has chosen in for analysis. So the length changes in, the breadth changes in, but all of the answers that are got with this can be put in a single graph, because the only criteria to meet in to create geometrically similar wiggly hulls are that the L by B ratio and B by T ratio should be within a limit. That is to L by B ratio should be 10 and B by T ratio should be 1.6. So similarly, I have also chosen a almost geometrically similar wiggly hull that I have highlighted in red, and that has been analyzed further in ship flow as well as OpenFlow. So first, the analysis for potential flow, that is to find out the wave resistance, has been shown in. So this is entirely dedicated on how it has been analyzed in ship flow. There are different Froude numbers that it has been analyzed in for, ranging from Froude number 0.2 to 0.4. And these are, since it is a potential flow solver, mostly the analysis depend upon the panels that are created in for analysis. So in potential flow, there are panels that are created over the surface of the hull to define the surface, as well as over the free surface, there are panels. And what determines on how much accurate results that we get in depends upon how good these panels are defined in. So these are, further on, I will be explaining on how these panels are chosen in for analysis of the wiggly hull. Now, this is something that has been said from the software side itself. If there are different meshes that are defined inside the software that are called as fine, medium, and coarse, that are used in automatically. That means the solver itself decides, depending upon the Froude number, what should be the finest mesh and what should be the coarsest mesh. And you can run in 3 cases just to find out what would be the wave resistance. But if we are to implement a new mesh manually, then I have taken out how much panels should be there depending upon the wavelength and the wavelength over the surface of the over the free surface. For that, I have calculated what would be the wavelength, and I have found out what would be the definitions that the software itself gives in when it says that it has got 20 panels over the free surface. So you can say that if you see the DLU part, it shows that what is the first cell thickness in the upstream. That is the explanation of these abbreviations. All these abbreviations are used in to define what are the meshes inside ship flow. For example, like XUPS is the distance to the upstream, X downstream, all those things are used to define in what happens over the free surface. Similarly, the first cell towards the upstream is defined as lambda divided by 32. I just normalized it depending upon what would be the wavelength. So for that, continuing, I made few other meshes. I have now shown 2, 3, and 4, but further many meshes were done between this fine and mesh 2
to come into where I got a wave resistance that is reasonable to compare with the experimental results. When I first did it with the fine mesh that the solver was defined as fine, it gave me a value very higher than what I have expected in. Then further on, reducing all these parameters one by one, I got in a value of 2.06, which is within a 2% difference with the experimental results. So what it got from here is that the fine mesh the solver itself sets isn't sufficient enough to get the wave resistance, the experimental to compare it with the experimental results of the wave resistance. Okay. So I did the same thing for other fruit numbers also. 0.2 was earlier done, and 0.3 and 0.4 were done. Sorry, 0.4 was first done, and 0.3 and 0.2 was done. At 0.4, it was at a difference of 2.8% with the experimental results. But as the wave height became smaller and smaller, it became difficult to compute in what was happening over the free surface. So there was a percentage difference higher as we went higher, lower in the fruit number. Yes. So this is the wave profile and a wave cut section at a distance from the central line. So taking out some conclusions from the ship flow is that first we were able to compare the results that were gotten for wave resistance with the experimental results within a percentage of 2.8 difference between the experimental. And then with further continuing it at fruit number 0.3 and 0.2, we were able to have in an analysis where the difference was within 4.4. As it became smaller, the fruit number, it was much more difficult to compute in. And thus, it was at a difference of 11% difference with the experimental results. The reason for that is because as the fruit number comes down, it becomes more and more difficult to compute in things. Once the ship flow analysis was done, the same hull was analyzed in OpenFOAM too. And these are the details on what were the settings that were given in OpenFOAM. 3 fruit numbers as similar to what has been used earlier has been done. A pseudo-transit solver and K omega SST turbulence model was used in. So the major part of what is done in the OpenFOAM was to analyze the hull very efficiently. And that is to create in a mesh that can solve for total resistance very accurately. So most of the effort went in this case to create a mesh that it can solve the total resistance accurately. And the conditions or the utilities in OpenFOAM that was used to give the inputs were defined over here. All the utilities that have been defined in Toposec, Snappy Hex, and Block Mesh, all these are OpenFOAM's utility that we use to define the cells in the domain. So what happened over here is also similar to what I did in ship flow. I decided the cells closer to the hull, depending upon the ITTC recommendation, that it should be at least 40 lambda divided by 40 cells around the surface of the hull. It should be fine enough to compute the wave profile accurately. And the wave height, we started off with where the wave height was approximately calculated at 1.5 LPP by 100, and then that was divided into 20 cells. This was a starting point. Once we run in an analysis, we can further on continue from it and then build up the next meshes. That was how it was done. And regarding this, about 12.6 million cells were created in. And closer to the hull, there are a utility called as add layer that has been used into accurately compute what is happening inside the boundary layer. And that first layer thickness is very important to compute what happens in the add layer. And that was also computed with respect to what happens that was given in ITTC. So these are what the results that I have got in with respect to OpenFOAM. A range of fruit number is being shown in. So I kind of computed or tabulated with respect to what the Y-wall plus was ranging in the 3 fruit numbers. So my aim was to get a Y-wall plus less than 5. In the first, where it is fruit number of 0.2, I was able to attain where the most of the cells around the hull, about 98% was inside in that layer. For the next 0.3 also, it was 95.7%. 0.4, it was slightly above, lesser than what I was expecting in. And these are the range of the percentage differences with the experimental results. And this is the wave elevation profiles that I've been showing. And as you can see, the drag plot has been, the aim is to attain in a graph where it can rapidly converge in. It should not diverge, it should not oscillate, but it should converge into a drag value that I can take in. So the aim was to create in a mesh that I can get in where the values are reasonable within a reasonable number of iterations. And these are the conclusions that I have got from OpenFOAM. A mesh was set up in that I can run in a hull where I can get in a reasonable value of total resistance. And this was in good agreement with the experimental results. And the values of differences are shown in, and the Y-wall plus that has been taken in is also shown. So the next one was to compare between the OpenFOAM and ShipFlow. Here I just have computed like how much percentage of wave resistance comes into total resistance with wiggly hull. Because in looking it in a larger view, the aim was to do it for optimization, not just for wiggly hull. So in order to do that for optimization, this was a preliminary step just done to analyze in how we can compute the wave resistance as well as to compute the total resistance and how we can quantify this between each other. And this is the comparison between what has been got from the potential solver and the viscous solver. So from the blue ones show what was attained from ShipFlow, that is the potential, and the red one shows what is happening in OpenFOAM. The blue one is in shorter length, the domain, everything that is chosen for potential flow is much lesser than that of OpenFOAM. But you can see that between 1 to 0, that is where the hull is actually, there is a pretty good agreement between the wave profiles at a distance of 0.1 LPP. So these are the conclusions. I have got a good agreement with the ShipFlow as well as in OpenFOAM analysis, where I can take in the values and compare with the experimental results. And I've quantified it with respect to CW to CT. And this idea of finding out wave resistance from ShipFlow and using it to compare with and to rank hulls and use it for finding out total resistance in OpenFOAM can further be used in analyze for other actual hulls, and the best one can be taken out from that. This is an acknowledgement. This has been done as part of a project that we had got from Cochin Shipyard as a preliminary analysis. Thank you.
Okay, thank you. Open for discussion. Any question? If one. I think we have only limited time. Anybody?
Hello, myself Sharath Raj. So for a turbulence model, you have chosen KMA SSC, right? So why you have chosen that particular turbulence model? You can use V square F, then LES, larger D simulation is there. Then K epsilon modeling is there. Then why specifically KMA SSC? One question. And the next question, you have done a mesh independence study?
Yeah, for one crude number, I have done mesh independence.
Mesh independence study. I think that graph you haven't incorporated in the presentation, right?
It's just one mesh that I have shown.
Oh, yeah. Okay. So regarding pressure velocity coupling, which algorithm or which solver or which algorithm you are using?
It's Pimple solver that has been used.
Pimple algorithm. Why Simple or Simplex or Piso algorithm?
So I'm using the pseudo transient. So there simple, I don't think will be an option to use it. Simplex, I haven't tried out with that.
Okay.
Right now, it is with Pimple that I've been using.
Okay. Okay. And regarding that turbulence model thing,
Turbulence
KMA
model,
gases.
LES, I haven't tried for it. Requires more meshing,
Yes,
more time, everything.
Yes, actually in three-dimensional simulation, LES give good results, larger D simulations, these kind of problems.
Yes, it is there, but
Uh-huh.
the finer the things have to be at LES,
Yes.
it's costlier when it comes.
Yeah, that computational cost is very much high
So I
for
couldn't
LES.
afford that. Between
Yeah.
K epsilon, K omega, right now I am trying it with hulls where it is more like skin friction coefficient, all those are where what happens close to the boundary are of more importance.
Okay.
So I need a finer layer close to the hull.
Okay. Thank
So
you.
ultimately it's K omega plus.
Thank you. Thank you.
Any other questions?
Can interact because it's running short of time. Thank you. Yeah. Yes. Yeah, Shrija. To finish 4 presentations in 40 minutes. So each one can take only 10 minutes. So restrict the presentation to 8 minutes. Okay, Shrija? 8 minutes presentation. Okay, please hurry up. Otherwise, people, they have to go for a trip, right? Right, eh? Is it okay? No. Oh, then it's okay. I'm not sure because they've planned for some trip or something. Okay. Tea is there. Okay. Okay, your 10 minutes, not more than 10 minutes. Okay. Yeah.
The Kerala State Council for Science, Technology and Environment, ETP funded project under which this work is carried out, is gratefully acknowledged. So the hydrodynamic performance of marine propellers, which is evaluated using open water test, and the open water parameters like thrust coefficient, torque coefficient, and efficiency, which are plotted against advanced coefficient. And these tests are usually conducted with high RPS and under the fully turbulent condition, and causing the Reynolds number to vary as advanced velocity VA and the advanced coefficient J should change. And here what I am doing is I want to find the effect of Reynolds number on these parameters. So I'm keeping my advanced coefficient J is constant, and the Reynolds number is varied from 10 raised to 5 to 10 raised to 6 for a car series propeller, and the analysis is using done by using Siemens star CCM plus CFD package. And I am for this study I am using the propeller of diameter 400 mm. Then why this 400 mm propeller? Actually, I am using this propeller for my AUV of diameter 533 mm. According to Moland, the propeller size, which is 0.75 times the AUV diameter. That's why I'm using this 400 mm propeller for my study. And the car series propeller 470 propeller, which is used for the study with a P/D ratio 1.2. And the J is kept constant as 1. And the Reynolds number changed from 1E5 to 1E8. So the open water Reynolds number, which is based on the resultant velocity, that equation shown in the slide, and the resultant velocity, which is based on the 0.75 r radius of the propeller. There is an assumption that the 0.75 radius propeller, which is assumed as a whole propeller. So here I am taking, I'm keeping the J value constant and finding the VR and VA and the rotation rate for my input values for the analysis. So these are the propeller open water parameters that we all know, the thrust coefficient, torque coefficient, and the efficiency. I'm looking into what changes these parameters will cause if the Reynolds number changes. So the methodology adopted is the CFD analysis using star CCM plus software, and K omega shear stress transport turbulence model is used to solve the RANS equation. And I'm focusing on finding the hydrodynamic performance of this propeller by changing the Reynolds number at constant advanced coefficient. And the softwares used are the CATIA modeling software is used to create the geometry of the propeller, and the commercial star CCM plus is used for the analysis. And the simulation technique, what I'm using is the MRF method. And here the propeller is modeled within the rotating region, and the surrounding region is kept stationary. And this method, which allows the steady state analysis of the flow field around the rotating blade, we don't need to do for time dependent simulation, because the flow around the propeller, if it is axisymmetric, we can go for MRF steady state method. And for the near wall treatment, I'm using K omega SST turbulence model with all Y plus treatment, and which enables the use of both fine and coarse meshes in the near wall region without sacrificing any accuracy. And verification is the process that we need to do for any analysis, and to check whether the procedure we are following for the CFD is accurate or not. So for the verification process, we will compare our numerical result with the published numerical result. So in the from the available literature, they are using a propeller of radius 300 mm. I'm using 400 mm propeller for my study. There is a slightly variation, slight scale effect maybe occur if I'm using 400 mm, if we compare with the 300 mm result. So for the verification procedure, I'm using 300 mm propeller. And the geometric details of that 300 mm propeller as in the literature is shown in figure. And this is the domain and the boundary details, which all are as per the ITTC recommendation. And this is the mesh details. And here the fine mesh is generated where high gradient occurs. And in star CCM, we are using prism layers to find the near wall region. And a total of 5.7 million cells are generated here. And the near wall thickness, which is provided, the 10⁻⁻5 meter here. And star CCM provides some mesh quality parameters, and the like skewness angle, phase validity, that's all shown in the slide. And this all under the satisfactory conditions. So, and this is the result for the verification. And from this table, it can see that the CFD shows good agreement with the published numerical result. And here, this is the graphical representation of the previous table. And there is a close agreement between the present star CCM plus and the published numerical result. And if we look into this graph and the analysis procedure, what employed for evaluating these open water characteristics of the propeller, which is sufficiently accurate to proceed to the other cases. So I'm following the same procedure for my propeller case. And here we are moving to the propeller car series 470, 400 mm propeller analysis. And here the Reynolds number, which is based on the resultant velocity that I have already mentioned earlier. And this is the geometry details of my 400 mm propeller. And the Reynolds number changes from 1E5 to 1E8. And this is the domain and mesh and the boundary condition, which all are as per the ITTC recommendation. And these all the mesh quality parameters, which all under the satisfactory condition. And regarding the convergence criteria, the analysis results are considered to be converged if the first 5 significant digits remain unchanged for the 1000 iteration. And when coming to result analysis, we can see that when the Reynolds number is less than 1E6, we can see there is a steep slope for this open water parameters curve. If the Reynolds number, which is more than 4E6, the curve gets flattened. So there is, for the open water test, beyond this 4E6, the Reynolds number, which is independent. So there is a table shown here. The percentage increase in this open water parameters as Reynolds number
increases is as follows. And here when 1E5 to 1E6, the KT, 10 KQ and efficiency value percentage increases are shown in the table. And when coming to 1E7 to 1E8, this percentage increase, which is decreasing. And so the uncertainty due to mesh is found out using Richardson extrapolation, and GCA value is reported as 0.55 percentage. And when coming to conclusion, for a Reynolds number less than 1E6, the open water curve shows large slope that indicate the dominant viscous effect. And that is at lower Reynolds number, the value of open water parameters that KT, KQ and efficiency are lower. And for a Reynolds number which is greater than 4E6, the curve is flattened and the performance which is nearly Reynolds number independent. And it indicates that the importance of correct RE when comparing model versus full scale. And these are my references. Thank you.
Okay, thank you. Just one quick observation. When you say Reynolds number is related to viscosity. Viscous effect is related to drag. Drag is related to KQ, torque and KQ. So Reynolds number effect should be more on KQ. I don't know whether it's going to affect the thrust part of it much. You keep that in mind. Okay. Any question?
So you were mentioning that your validation was with a published numerical result. So this published numerical result was done with the same software, or
No, sir. That's
can you just
And-
how it is done?
and-
Using which software or which equation?
No, sir. They are using some code software. They're not means they're code CFD code software.
Okay, okay. But the
Not
same.
mentioning any the CFD software they're using. They're using some codes like open source code like that. Their own code they are using for the simulation.
Yeah, they
They-
they are not using commercial software.
Yes,
They are based on
They're-
some,
Yes.
but the same geometry.
Yes, sir.
Same geometry.
Yes, sir. Yes,
And all other boundary condition, everything
Yes.
is same as that of your work.
Yes.
And you have compared the star CCM result with that paper.
There.
Okay.
Yeah, if no other questions, so we move on to the next presentation. Thank you. Rasima? Yeah. Rasima, okay. No. Spell. Say. How do you spell? Ras. MIA. Okay, it's a typing mistake. Let's go.
After 8 minutes, you will have a single bill. Then 10 minutes double.
Good evening, everyone. I'm Rasmia PLE, representing paper ID 116, a research scholar of the Department of Ship Technology, presenting the paper, Quick Estimation of Resistance with Acceptable Error, co-authored by Sadish Babu PK, Manoj T. Isaac, and Dr. Didier Benesri. So these are my contents for today. We'll start with introduction, followed by domain, mesh, results, discussion, and references. The shipping industry transports about 90% of the world trade, and the design, analysis, and manufacture of ships is a very complex task. Time, money, and computational capabilities are always optimized to get the desired output. The cost of estimation is the time taken. And starting from the preliminary design stage to the final sea trials, the resistance estimation is done by many approximate methods and with the associated errors. Here, a benchmark hull is used to find the total resistance with the objective of finding a minimum cell count and time requirement. The requirement of the industry is minimum time, minimum error, more or less agreeing to the ITTC conventions. Discussing about the geometry, the CRISO container ship hull at a model scale of 1:31.6 at a Froude number of 0.26 is simulated to find the total resistance. The LPP is 7.2786 meters and it is a benchmark model and the results are widely available. Now we'll discuss the domain and boundary condition. The origin is at the intersection of the still water surface and the aft perpendicular. This aft perpendicular is at 0.341 meter above the keel and the domain extends 2.5 LPP towards the inlet and outlet from the origin. And the top boundary is at 1.2 LPP and bottom and lateral boundaries are at 2.5 LPP from the origin, all in accordance with the ITTC requirements. The upstream, top, and bottom boundaries are given as velocity inlet boundary condition. Outlet is given as pressure outlet. The lateral boundary is given as a symmetry plane, and only half of the geometry is modeled due to symmetry conditions. So the idea of meshing is to capture the Kelvin-Wick area and also the boundary layer flow. For Kelvin-Wick refinement, we refine the region near the free surface. For refining the capturing the boundary flow, we have the prism layer. And the gradation from coarse to fine is given by introducing cylindrical and cubical refinement volumes for volumetric meshing. The mesh is made finer where the wave is expected and also in the regions with steep geometrical change. Trimmed hexahedral meshes with refinements along the bow region, the stern region, and prism layers along the wall are used for meshing. This is showing the top view of the mesh. You can find the gradation which shows the refinement required for the Kelvin-Wick. This is showing the side view of the mesh. You can see the free surface refinement given. Apart from the mesh metrics that is provided by the software, I am using Star CCM software. The chevron quality, skewness angle, phase validity, etc. are the mesh quality metrics provided by the software. Apart from that, mesh metrics like NK, NW can be defined for the core mesh. I'll explain what that is. In the Kelvin-Wick region, the lateral size of the cells are expressed as a fraction of the Kelvin-Wick length lambda. And the cell sizes are expressed as lambda by NK, where NK is an integer. In the vertical direction, near the air-water interface, the cell heights are expressed as HW by NW, where NW is an integer. HW is the approximate wave height, which is 1.5 LPP by 100, an approximate estimation of the wave height. NK and NW, all those we were discussing about the core mesh. Now we'll discuss three more factors which can be the metrics that can be used for the prism layer. First one is the median value of Y plus, P5, the percentage of cells with Y wall plus value less than 5, Y95, the 95% of values of Y wall plus are below this upper bound. These metrics can be used for the prism layer region. So these are my table showing the mesh quality details. We have three meshes, mesh 1, mesh 2, and mesh 3. Mesh 1 is a coarse mesh 2 is medium, and mesh 3 is fine. And we have the total number of cells as 0.5, 1.5, and 2.8 million cells respectively. And I'll discuss the boundary layer refinement. A stands for the first layer thickness, R is the rate of growth, N is the total number of layers, and Sn is the total thickness of the boundary layer. Next, we'll have the Kelvin wake refinement details, NK and NW, which were discussed earlier. These are the statistics of the Y wall plus. The median Y wall plus, we are discussing median Y wall plus. Why? Because there may be outliers, bigger values of Y wall plus with a very few percentage. We need not be considered about that, because we can continue that work because our time, we are more focused on less time. So with that, we can keep the outliers. We do not want to consider the outliers. That is why we have coined a median Y wall plus term here. This describes the physics of the flow. We used steady Reynolds average Navier-Stokes equations. The simulations that include unsteady effects or dynamic fluid body interactions will give us more accurate results, but takes much more time. Two turbulence models, K epsilon, K omega SST, were used to find the results. The average value of coefficient of resistance, the experimental value, is 0.003711 for Froude number 0.26, as quoted from the Ship Hydrodynamics workshop of 2015. For both turbulence models, as the mesh becomes finer, the difference between the computational fluid dynamic resistance and the mean of the experimental fluid dynamic resistance, which is the error, decreases. The K epsilon model consistently yield a lower error than the K omega model. This is showing the Kelvin wake pattern from the analysis. These are the results. The table shows for the mesh. And we have, I'll show you this one. This is how we get the result. It is a quietly oscillating and staggered result. From that, what we take is what we think is a stable portion of the result, and find an average of the peaks. So the mesh, this table gives us from which iteration the result is taken, the average value of resistance, and the error percentage. You can also see the maximum percentage error is 10. Analysis with mesh 1, which has only 0.5 million cells, and the K epsilon model yields an error of 6%, which is the crux of the method, minimum time and minimum error. Using larger meshes 2 and meshes 3 further reduces the error to 5% and 3% respectively. The difference, coming to my conclusions, differences as low as 6%, 5%, and 3% between the resistances obtained using CFD, and the mean of experimental fluid dynamics are obtained using 3 meshes for the benchmark KZS. Only 0.5 million, 1.4 million, and 2.8 million cells are used. Steady analysis and the K epsilon turbulence model are used to save time, and this example shows similar lock-on meshes can be very useful for the preliminary design of a ship. Thank you.
Yeah. It's open for discussion. Okay, maybe I'll start that. Just where you say it's a quick method to
Quick with respect to other methods. We have unsteady method. We can also do dynamic fluid body interaction. So the industry requirement is to get acceptable results within a limited time frame. If we are using other methods, we'll get even accurate results, maybe 2% or 1% error results.
what I said is maybe so I don't know whether about this the body dynamics also coming in here. So what I suggest is at least keep maybe the time computational time. Okay, when you say quick, it's related to time. So when you say you have used the word quick, isn't it? Quick estimation. Maybe you find out how's the time for different methods.
Yes,
The
yes.
time
It is
compares-
approximately half from.
Yeah, that's what I'm saying. That may be better to give the time and of course other computation aspects. And when it comes to the K epsilon and K omega SST model and all that, these models are meant for different, applications basically. Of course, they're all turbulent models. And I find that you reported K epsilon is giving better value. There must be a reason for that. And maybe instead of just reporting the observation, you have to give an explanation why it's so.
Okay, sir.
So that's important when it comes to results. It's not just reporting observation, but tell also why it's happening. Okay.
You were mentioning that a total thickness of the boundary layer in that. How what is the quantity coming? Yeah, here. So the thickness is, total thickness is how much? Oh, yeah. How you are tracking the boundary layer thickness? How? Okay. Oh, you are giving the boundary layer thickness initially. How you are ensuring that that is the edge of the boundary layer? You are validating in between. No, you are giving us input the boundary layer thickness, but actually whether the boundary layer lies there or not, how you can ensure?
Again, let me measure, or we are actually setting the parameters such that it should come to that SN should come up to that value.
Okay.
The A value, the number of ratio, it is actually a geometric progression value. So these numbers has to be this one. The A has to be this, R has to be this, then SN has to be this.
Okay, my question was that you are giving that as input, and whether you are ensuring that itself is the edge of the boundary layer.
We can measure the details, and in spite of that, the numbers are such a way that it is a geometric progression. So it will come out to be the total.
So you were referring that this can be used for the basic design or the first few iterations in ship design. This method can be applied on your final conclusion slide. You have mentioned, right? So my doubt is, this is this methodology you are applying for a conventional hull form, correct? So there are already established methodic series available, model tested results, which can be used to find the total resistance of the bare hull. Correct. So what is your defense using this system? I mean, this particular CFD approach. Secondly, I was wondering whether this can be used for unconventional hull forms, for which naval architects will not be able to estimate the resistance. For unconventional hull forms, say for example, unconventional hull forms in which we will not be able to, establish the resistance by using the methodic series. So we may have to exercise some other alternative. So my question is, what is your defense on saying that this can be used for conventional hull forms? Secondly, whether these results can be applied to a unconventional hull form in which you can exempt your model testing procedure.
For unconventional hull forms, we need methods that is specially formulated for that. This method we can use. This is a basic idea of how fast or how we can get a preliminary result. For unconventional hull forms, we need more specialized methods or measures that for something similar to this can be used. For an unconventional hull form, anything existing won't be enough. We'll need more methods now for unconventional. A very different hull form would require something.
No, but if it is a conventional hull, you can use either Hull Tropane or Guldama Harvard
Series 60 or existing, those results you will be able to easily calculate and find out the approximate estimation of the resistance in the bare hull condition.
Yes.
And for which you will be adding the allowances for your roughness or your, rough sea conditions, air resistance, those things. So that can be done. So why you want to spend so much of time and resources to go for this CFT approach for a conventional hull form? That's what I'm asking.
But the resources spent is not much. This is pretty easy to do this after the first.
Okay, so the next stage can be used. Next, the stage you will be able to, use this for specialized hull form. That's what your defense is.
Yes.
Okay.
His question is related to why are we not using regression analysis results? Okay. So regression analysis result do not tell me what will happen if I change the hull form a little bit. It's just based on length, breadth, draft, and the parameters. It does not depend on the actual hull form. Whereas this result depends on the actual hull form. So if you want to change your LCB a little bit and then find out the resistance, you can do it this way, but you can't do it with regression analysis. And regarding unconventional hull forms, maybe you have to mesh it with little more care, but in essence, it is the same method. And today, I think we should not rely on just regression formula even for preliminary analysis. I think that is 1985 based, right? Hmm. Yeah, yeah. Mm. 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 Mhm. Yeah, actually, there have been various regression formula over the decades. And these regression formula have been developed for certain types of hulls. Today, the hull is much different from what it was in 1980. Therefore, we should not be using that formula. You may still get some small error, maybe 5–10%, depends on what you want. Without using regression formula also, I can find out what the resistance is. It may have only 10% error. So I think we need to spend time and effort developing better methods, which will lead on to improvements. We cannot live 50 years old.
Yeah. Okay. Thanks for the presentation.
Thank you, sir.
Yeah. Give a clap to her. Next presentation, we move on to Adina. So you know the system here, right? 8 minutes.
Good evening, all. Today I am here to present the study regarding the parametric representation of ship hulls using NURBS. This study was conducted as a part of project funded by Cochin Shipyard Limited. Overview of the presentation that NURBS means non-uniform rational B-spline. That is a mathematical tool to define curves and surfaces that some naval architecture softwares like Rhino, MatSurf, Shipflow, etc. are using NURBS for hull modeling and optimization. And here, this study begins
by analyzing some basic curve generation methods such as cubic spline, Bezier curve, and B-spline. And these curves have some limitation. To overcome this limitation, NURBS are introduced. And I fitted NURBS curve to some hull sections and also generated NURB surface of wiggly hull and compared this wiggly hull NURB surface with the analytical, that normal surface. And first I am explaining about some basic curve generation method. First is the polynomials and cubic spline. Polynomial curves can pass exactly through multiple points. Here, this figure is the curves fitted to an arc station. Here, that red dashed line shows the 6-degree polynomial. Here, at the point 2 and 3 and at the point 7 and 8, this 6-degree polynomial shows higher oscillation. So, they are not used too much. And this blue solid line shows the cubic spline. Cubic spline is composed of several third-degree polynomial. This is the equation for the third-degree polynomial equation, that for a segment, we have 4 coefficients. So for n segment, we have 4 n coefficients, and we need 4 n condition to solve these equations. So for finding out these coefficients, we need C0 continuity, C1 continuity, C2 continuity, and some boundary conditions. And disadvantages of cubic spline, that cubic splines pass through all the points. So in hull design, the exact full set of points is often not known in advance. So this limits its direct use. To overcome this limitation, the Bezier curves are introduced. The Bezier curves, that is an approximating spline. That means the curve pass through the first and last control point, and intermediate point act as influences that determine the shape of the curve. Here, this figure is the third-degree Bezier curve. This is the general equation for Bezier curve, that P is the coordinate value. That is the control point that determines the x and y coordinated in 2D. In 3D, that's x, y, z coordinates. And here, the second and third point determine the shape of the curve. And disadvantages, that the main disadvantage of this Bezier curve is the global control, that moving any control point affect the entire curve, not just the nearby portion. Here, in this figure, this red dashed line shows the initial control polygon, and the black solid line is the initial Bezier curve. When we move a control point from this to this, then the entire curve is changing. That is shown in that blue solid line, that is modified Bezier curve. And here in Bezier curve, number of control point and degree of polynomial are related. That is, number of control point minus 1 is equal to degree of polynomial. That means when we model a complex structure, when we have 100 or something control point, then we need 99th degree of polynomial. That is inefficient. So, and next, limited shape representation. And this Bezier curve can't represent conic section. Rational Bezier curves can represent, but it have the above disadvantages also. Next, to overcome these limitations of Bezier curve, the B-splines are introduced. B-spline means basis spline. That is constructed from one or more curve segments. Here, this is the B-spline curve, that each segment of the spline join at points called nodes. This red dot is the nodes, and each curve segment is represented by a polynomial of degree k minus 1. K is the order of the spline, and here the order of the curve or degree is less than number of control point. And this B-spline does not pass through any of the control point. All the control point act as influences. To make it to pass through the first and last control point, we need clamped spline. That means when we use the node value, repeated n node value, that is T, then we get the spline pass through the first and last control point. That B-splines is uniform when the interior nodes are equally spaced. When it is non-uniform, that when the interior nodes are unequally spaced. This is the general equation for B-spline. And here, this n are the basis function, and u is the spline parameter, varies from 0 to 1. And this is the equation for basis function. And this is the these two figures shows the basis function of uniform and non-uniform B-spline of degree 3. That's order 4. And these basis functions are non-zero only over specific node spans. Here, for each segment, the basis 4 basis functions are non-zero. And that means that each curve segment is locally influenced by k consecutive control point. K is the order of the curve. This is the example of B-spline. First one is the degree 2 and second one is the degree 3. Here C0, C1 continuity is there. Here C0, C1 and C2 continuity is there. Next, NURBS, non-uniform rational B-spline. NURBS are the extension of B-spline with an additional weight W assigned to each control point. This is the mathematical formula of NURBS. Here, when we want to control the shape of the curve, we have two methods that we can move the control point, that is P, or we can increase or decrease the weight value. Then we can change the curve locally. And I fitted the NURBS curve to hull sections of the given hull from CSL. That I used clamped uniform node vector, and weights were initially set to 1, and the degree of the curve is taken as 3. These are the curves. First one is the NURBS curves of midship section of the hull. Second one is the forward section of the hull. That here, the blue solid line shows the NURBS curve, and the red dashed line shows the control polygon. That from this figure, we can conclude that NURBS can represent simple and complex shapes easily. Next, NURBS surface. That NURBS surface is obtained by taking the control net in the two directions, that U and V direction, and the node vectors and the product of basis function in both directions. This is the equation for NURBS surface. And here also, when we increase the weight, we can pull the surface towards this control net. That in each direction can have its own degree and node spacing, allowing flexible shape control. Yeah, this is an example. This one is the control net and this one is the NURBS surface. Here, for this 4 control point, the weights are equal to 10 and rest of the weights are 1. And here, the curve, the NURBS surface, here, because of this higher value of weight, the NURBS surface is pulled close to this control net. Next, I have generated wiggly hull using this NURBS surface. And I used, this is the general equation of wiggly hull. I used clamped uniform node vector. And I compared this NURBS surface with the normal analytical one. That I used 10 division along the length and 5 division along the draft for generating this surface, this coarse surface, and this NURBS surface. Here we can say that the NURBS surface is smooth. That is because the NURBS is not depends on the number of division along the length or draft. It only depends on the number of elements in the parameter array. Here I used 30 and 15 as the parameters. And the NURBS shows good agreement with the ultra-fine one. I generated ultra-fine one using the 80 division along the length and 40 division along the draft. And NURBS surface for complex hull shape. When a hull shape has a complex shape with convex and concave region, it is difficult to represent the entire hull using a single NURBS surface. So the NURBS surface the hull is divided into several nerve surfaces. That is called patches. That means, for example, in bow region or in mid body or in stern region, we can use different nerve surfaces, and each patch is defined by its own set of control point, node vector, and parameter array. And these patches should be continuous at their interface with other patches. That means it should satisfy C0, C1, and C2 continuity. And to check these levels of continuity, the tools such as MathSurf, Surface Continuity Managers are used. Conclusion, a detailed study of classical curve methods such as cubic spline, Bezier curve, and B-spline, and it shows their limitations. And using the coarse offset table, I have generated nerve surface and compared it with the normal analytical one, and it shows good agreement with the ultra fine analytical wiggly hull surface. Future works based on this generated nerve surface, hull variants can be created and analyzed in ShiftFlow. The total resistance of the top ranked hull forms can be computed using OpenForm to identify the hull with the minimum resistance. These are the references. Thank you.
Okay, thank you. It's open for discussion. Any questions? Yeah, I'll start with that. So when you say, I've seen some ship section forms, two-dimensional. When you generate, you're trying different methods, different polynomials and nerves and all that. So what are the constraints you give for that section? So you have to know some constraints to the form, isn't it? Not a question. I'm saying, so suppose you know the section, the ship section, a section area is defined. Maybe it's a vertical centroid position is defined, or the centroid in transverse direction. So there are some constraints to the form. So sections, yeah. So you have to follow that. You cannot just compromise on that. So given with this, you have to come with a suitable form. So are you keeping that in your form generation? No, keep it. If you're not, you just think about it. I'm just giving as a feedback or my input. So also when it comes to a three-dimensional form, which said finally, all these things, you have to know vessel is designed, it should have so much displacement, your expected LCB position, longitudinal center of buoyancy position, with the plane, LCF position, all these things are supposed to be known. And so within that, how you come up with the, so first thing you have to look at is not hydrodynamics. First you have to look into hydrostatics. Ship should float and should float even keel. So there are many things to do. After that only you come, this a stable platform is there. Okay, then you look into hydrodynamics, resistance, motion, maneuvering, there are many things. So keep that in mind, because particularly you are working in naval technology department, but try to evolve it from the basics. Look. Yeah. Thank you. I think there's no other question, so thank you. And give a clap. Okay, we move on to the next and last presentation of the day. That is by Mr. Arjun. Yeah. Arjun, you know the timing, 8 minutes. You get that.
Good afternoon to all. Myself Arjun. I'm here to present the topic on inviscid wave resistance using ShiftFlow. This research is conducted as a part of a study which is funded by Cochin Shipyard Limited.
These are the overview of my presentation. So introduction, inviscid wave resistance of the KCS hull, shift flow, which is a shift flow expand, boundary panels, mesh settings, and mesh calculation, result, conclusions, and references. So as you all know, the ship resistance plays a major part in naval architecture. It is a major task. So it influences the propulsion power, fuel consumption, and overall vessel performance and all. So in traditionally, we are calculating the ship resistance as a model testing in a towing tank. So nowadays, the computational fluid dynamics is popular, which is a powerful alternative to the experimental one. And in this study, I have major focus is given into the inviscid wave resistance calculations. So first, the ship flow, the software which is used for this study. So for the inviscid wave resistance calculation, I have taken KCS, which is a standard benchmark model, and the ship data is given. I have analyzed for a fluid number of 0.26. For that, design speed was chosen as 24 knots, and the computation is done for free surface with sinkage and trim. And the density of freshwater is considered, and the density is chosen as 118.21 kilogram per meter cube. Then these are the software shift flow. It is an inviscid flow which uses an expand, which is a solver which is present in the shift flow. It uses a boundary element method, and generally we all know that wave resistance is obtained by subtracting two large quantities of the pressure which is acted on the different part of the hull, and the even tiny numerical error in these large quantity will give a large change in the errors in the wave resistance. So these already talk about Larsen and Ravenis already talk about this in their book. And in shift flow, by using expand, we could rank the hulls variance more reliably. And so by using expand, shift flow can rank the hull form according to the wave resistance. And here the approach is taken: first generate the panels on the hull surface and the free surface. Then the potential flow solver, that is expand, is used. Then find the viscous inviscid wave resistance, calculated the RW, then coefficient of wave resistance is calculated. So these are the panels. That is here in case of viscid solvers, they are using the cells. Here panels are considered. The panels is formed on the free surface and the hull region. Here this figure represents the panels that is formed on the hull region. In shift flow, there is software provide the custom mesh options like coarse, medium, and fine with respect to the fluid number which was given, and the domain is also chosen with respect to the fluid number by shift flow itself, and all the hull which is important to shift flow, which will be converted into unit length by shift flow itself. It will scale down every hull to 1 meter. So these are some abbreviations which is used in shift flow for the mesh. And here XUPS is the upstream length. XUPS is the upstream length, and X downstream is the XDOW is the X downstream section length, and Y4 side is the length of the domain in the transverse direction, and this is the top view of the domain. And so shift flow itself provides structure factor. In the software itself, there is a 5 structure factors: 0, 1, 2, 3, 4, and 5. In my analysis, I have chosen 1 and 5. 1 is applied in the free surface and 5 is given for the hull. The default domain size, the shift flow taken is upstream length is 4.4, downstream section is 2, and transverse side it is 1 meter. So these are the different mesh settings I have applied. For first 3 are the main default settings, which is present in the ship flow, which uses the fine order panels, and the fine mesh will give you the mesh or number of meshes in the fine. It will be twice the number of the mesh which is in the coarse mesh. For mesh 4, 5, and 6, the order of the panels will be changed to higher order. For mesh 7, the fine mesh settings is considered as a base mesh, and then the number of cells, number of stations, or number of panels is doubled. For mesh 8, the size is kept, the boundary is increased by 50%. And for the mesh 9, with the settings 3 is used, like fine mesh is used, and then the domain size is increased by 100%. For mesh 10, 11, and 12, mesh 7, 8, and 10 is used as a base mesh, and changed the order of the panels to higher order. So these are mesh settings, meshing and mesh calculation as done in ShipFlow. So I have taken here as a fine mesh, and here DHs represent the this length of the panels in the midsection, which is these panels. So the hull is here. So the midsection is start from here to here. So all the length of the panels which will be given is will be chosen by ShipFlow is 1.4 e raised to -2, and the panels on the last cell of the upstream section and the first cell of the downstream section, which will be same as the length of the panels in the middle, and the growth ratio is applied accordingly. So these are the mesh formed on the free surface. This is the top view of the free surface, and this is the mesh formed on the hull. Then these are the different mesh settings and the CW values given. For coarse, medium, and fine, 3.3, 3.8, and 4.0 e raised to -4, the values get. For mesh 4, 5, and 6, higher order panels are used, and the values drastically increased from the when using the panel type as first order. So for mesh 7, fine mesh is used as a base, and here the number of points and stations is doubled, and we are using the first order panels and giving a CW of 4.5 e raised to -2. Then for mesh 8, the length of the domain is increased by 50%, and the CW is given as 4.1 e raised to -4. For mesh 9, the domain length is increased by 100%, and the CW value is decreased to 3.8 e raised to -4. For mesh 10, 11, and 12, the higher order panels are used, and the CW is increased from the parent meshes. So for further comparison, the wave profile is along the hull surface is taken into consideration, and the experimental data is shown as blue dotted line, and the CFD data, which is obtained from the ShipFlow, is represented by the blue solid line. And from here we could say that the data is the curves are pretty good agreement with each other, in phase and the amplitude. It's indicate the potential flow solver can accurately predict or reproduce the wave patterns. And there is minor errors which is in here, these regions, which is due to the experimental uncertainties and the viscous effect, which is not considered here in potential flow. As conclusion, the in-visit analysis of the KCS has done for a Froude number of 0.26 and giving a CW of 4.03 e raised to -4. The 12 different mesh were analyzed with different mesh settings of how to check how it influences the in-visit wave resistant coefficient, so that the density, higher order panels, and the domain segmentation has done. As predicted, wave resistance coefficient does not show any significant convergence, and fourth, and increasing the domain length and performing other tasks like using higher order measures, which will not give you a meaningful improvement. And for further studies, fine mesh will be considered as the base mesh. For comparison, Dogrel is already reported a CW of 4.22 e raised to -4, which is close agreement with the fine mesh result. And the comparison of the wave profile along the hull surface of the case here shows a very good agreement with experimental result. These are my references. Thank you.
Okay, thank you. Yes, so please show that conclusion slide. The last one. Conclusion. The conclusion, that is towards the end. Just before the, yeah. So you're saying CW is 4.033 into e power 10 raised minus 4. And for a fruit number of 0.26. That's not correct. Yet, no, wave resistance, I don't think it's correct. It is a ship which is a fruit number 0.26. Wave making is significant. I know it's gaseous. It should be minus maybe 10 power minus 3. Then
For total resistance, right?
Eh?
It's only including.
No, you checked it. This is my
I
doubt.
checked with the paper by Google and
I have very strong doubt about it. It appears to be very low for me. 10 power minus 4. Huh? You check it, and also I suggest repeat the calculation with Goldhammer-Howell. Goldhammer-Howell gives a wave making resistance, right? CR, residual resistance. Goldhammer-Howell. You know the method. You're not a naval architect. Okay, so you contact some naval architects. It's a Goldhammer-Howell method. It's a straight method, easy method. So you check that and compare with it. One thing. And the second thing is, this is basically a ship resistance problem. Is a boundary value problem. You have to have an idea.
What boundary value? It's boundary is not considered here.
No, you listen to me. What I'm saying. We call it a boundary value problem. That means you have to specify the boundary conditions. That the ship is there, water around. What are the boundaries you are studying? Bottom is there. It's a boundary. Resurface, upper surface is a boundary. The boundaries away from the ship on the sides and the ends. All these are boundaries. Okay. There are physical conditions applied at these boundaries and also inside the domain. And there are mathematical relations for that, based on which this software is generated. You cannot use the software alone. You're doing research. You cannot use the software as a toolbox and giving some input and taking some output and put it here. That is not the right thing. Understand what is the physics behind it, what is the mathematics behind it, and how the software is written, what is the numerical method used in the software. Okay. And so all these things you have to look into. When coming to numerical method, you use the panel method. Panel method is using Green's function. Green's function is undefined at origin of the source or at r is equal to 0. So it has got a problem called irregular frequency. You look to the software, how this irregular frequency is tackled in software. See, this is, you have to go into the details. It's a well known. It's maybe many decades ago, it has been derived and put. So when you use the software, my suggestion is understand the physics, mathematics, numerical methods, what all things are being used, then only you can contribute to that. Otherwise, like a technician, you give some input, you take some output and reproduce it. So that won't become research. Okay. So anybody else? Okay, thank you.
By this, we are coming to the end of the afternoon session, session 2 of the day 1 of iCANOE 2025. Now we are handing over the participation certificates for the participants who have covered the forenoon and afternoon sessions today. So I invite convener Hasina ma'am, Beena ma'am and Arvind sir to please come forward to give away the certificates. Check. Rajan. I'll be calling with the paper IDs. Paper ID 111, Nantana Goban. ID 113, Sharath Raj. ID 114, S. Sruthi Raj. I invite Rajesh sir to come forward and give the rest of the certificates. ID 115, C. Shija. ID 116, Rasmia P. Ali. ID 117, Adina Anolat. ID 171, M. Arjun. Now, I invite HOD Madhyagan sir to come forward to give certificates for the chair and co-chair. I also invite Krishnagutti sir to come forward and receive the certificate for the chair of the session of day 1. Next, I invite Manoj T. Isaac sir to come forward to receive the co-chair certificate. Next, I invite Dr. Fawaz TK sir to please come forward and receive the certificate. By this, we are coming to the conclusion. We are actually planning to have a voyage in Kochi Metro. Those who are interested can please inquire with the registration desk for the details and the registration. Thank you. We are winding up. High tea is provided outside.